Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are drifting toward one of the quietest and most stubborn mysteries in all of astronomy. A mystery so large that it surrounds every galaxy we can see, yet so shy that it has never once stepped into the light. We're talking about dark matter, the unseen material that seems to hold galaxies together, guide the growth of cosmic structures, and make up much of the matter in the universe, while refusing to announce what it actually is. That is a rather strange place to begin, is it not? Most things in science introduce themselves in some way. Stars shine, planets reflect, gas clouds glow when they are warmed, dust blocks starlight and leaves shadows. Even black holes, famous for being difficult dinner guests, reveal themselves by the hot matter swirling around them or by the way they bend light nearby. But dark matter does none of the usual things. None of. It does not shine, does not sparkle, does not form a helpful little label saying, "Here I am." It appears only through its gravity, like an invisible hand gently pressing on the universe from behind the curtain. Before we wander too deeply into that curtain, I would love to know where you are listening from tonight. Are you somewhere under a bright city sky, where only the strongest stars manage to peek through, or somewhere quiet and dark, where the Milky Way looks like spilled flour across the heavens, and if you look outside right now, even for just a moment, what does the night look like where you are? Cloudy, clear, moonlit, or perhaps simply hidden behind the comfortable walls of a room that has finally become still? If this gentle journey helps you relax, learn something curious, or settle into the soft edge of sleep, I would be very grateful if you gave the video a like and subscribed. It helps this peaceful little corner of physics reach more people who might enjoy a calm voice, a strange universe, and the reassuring thought that no one fully understands everything, not even professional scientists with very serious chalkboards. And perhaps that is a comforting thing. The universe is not a finished book with every page explained. It is still full of missing paragraphs, smudged notes, and whole sections written in ink we have not yet learned to read. So settle in, loosen the day from your shoulders, and let us begin with a simple picture. Imagine a great spiral galaxy hanging in space. It has long arms of stars, soft lanes of dust, glowing pink clouds where new stars are being born, and a bright central region packed with ancient suns. It turns slowly, almost too slowly to imagine, taking hundreds of millions of years to complete a single rotation. If you could watch it from far away, sped up like a time-lapse of clouds crossing the sky, it would look graceful and balanced, like a vast luminous pinwheel. Now here is the odd part. When astronomers measure how fast stars move around the centres of galaxies, they find something that does not quite make sense if only visible matter is present. The stars near the outer edges are moving too quickly. They should not be so well behaved. They should not remain so neatly bound to the galaxy. With only the gravity of the stars, gas and dust we can see, many of those outer stars ought to drift away, like children spinning too fast on a playground roundabout and losing their grip. But they do not. They keep circling. The galaxy holds together. Something is adding gravity. Not a little something, a great deal of something. This is one of the first clues that dark matter exists. It is not a clue in the sense of a single mysterious footprint by the garden gate. It is more like waking up to find that every garden gate on Earth has the same strange footprint beside it. Galaxies across the cosmos behave as though they are embedded in vast halos of unseen matter. These halos extend far beyond the bright visible disks of stars. The luminous galaxy, beautiful as it is, may be only the glowing centre of a much larger invisible structure. That idea can feel upside down at first. We're used to thinking of galaxies as the visible things in pictures, the spirals and ellipses and shimmering starfields. Dark matter asks us to imagine that what we see is not the whole body of the galaxy, but more like the foam on top of a deep sea. The stars are the glittering surface. Beneath and around them is something larger, quieter and hidden. The name dark matter sounds dramatic, almost theatrical, as though it belongs in a story with secret chambers and suspicious footsteps. But the word dark simply means that it does not interact with light in the usual way. It is not dark like black paint. It is dark because our telescopes do not see it directly. Matter, meanwhile, means it has mass and produces gravity. It is not just empty space. It has an effect. It pulls, it shapes, it leaves evidence. And this is where science becomes both careful and wonderfully strange. Scientists did not invent dark matter because they wanted the universe to be more mysterious. They did not add it to the story as decoration. They were pushed toward it by observations. Again and again, when they tried to explain how galaxies rotate, how galaxy clusters hold together, how light bends around massive objects, and how the largest structures in the universe formed, the visible matter was not enough. The numbers kept coming up short. The universe seemed to be heavier than it looked. There is something gently funny about that. The cosmos, with all its blazing stars and enormous galaxies, has been quietly telling us that it is mostly not the part that glows. We built telescopes to gather light, and light rewarded us with magnificent images, nebulae like painted clouds, galaxies like lanterns in deep water, star clusters like spilled jewels. But then gravity tapped us politely on the shoulder and said, "Yes, very pretty, but you are missing most of the furniture. Dark matter is not just a small correction. It is not like discovering that a suitcase weighs a little more because someone left a pair of socks inside. It is more like weighing a house, counting only the curtains, lamps and teacups, and then realizing there must also be walls, floors, beams, and foundations you somehow cannot see. The visible universe is not fake or unimportant. It is very real. It is where stars burn, planets form, and living things ask questions. But it appears to be built within a much larger gravitational framework. That framework matters deeply. Without dark matter, galaxies may never have formed in the way they did. In the early universe, ordinary matter was hot, restless, and strongly tied to radiation. It could not easily clump into stable structures at first. Dark matter, if it behaves the way most models suggest, was able to begin gathering under gravity earlier and more quietly. It formed invisible wells, regions where gravity was slightly stronger. Ordinary matter later fell into those wells, cooled, gathered, and eventually made stars and galaxies. In that sense, dark matter may have been the scaffolding around which the visible universe assembled itself. Scaffolding is not usually the part of a building people admire. Visitors do not stand in front of a cathedral and say, "What splendid temporary metal supports must have been used here." They admire the stone, the glass, the arches, the carved figures. Yet without support during construction, the structure could not rise. Dark matter may be something like that, except the scaffolding never left. It remains around galaxies, around clusters, threaded through the universe on scales so large that the imagination has to stretch before breakfast just to keep up. One of the most striking pieces of evidence comes from galaxy clusters. These are enormous gatherings of galaxies, sometimes containing hundreds or thousands of them, bound together by gravity. Between the galaxies is hot gas, so hot that it shines in X-rays. When astronomers study clusters, they can estimate how much ordinary matter is present in stars and gas. Then they can measure the total gravity of the cluster by observing how it affects the motion of galaxies, or how it bends the light from objects behind it. Again, the visible matter is not enough. The cluster behaves as though much more mass is there. This bending of light is especially useful. Einstein showed that mass curves the space around it, and light follows that curvature. When light from a distant galaxy passes near a massive cluster on its way to us, the cluster can bend and distort that light. Sometimes it stretches the background galaxy into arcs. Sometimes it creates multiple images of the same distant object. This effect is called gravitational lensing, though we do not need the technical term to appreciate the idea. Space itself behaves like a lens when enough mass is gathered in one place. By studying those distortions, astronomers can map where the mass is, including mass they cannot see. Here, dark matter leaves something close to a silhouette, not a shadow made by blocking light, but a gravitational outline drawn in bent starlight. It is as if the universe has placed invisible glass in front of us, and we can tell it is there because the view behind it warps. That is one of the quiet beauties of astronomy. Sometimes we learn not by seeing a thing directly, but by seeing how everything around it responds. Still, the central question remains: what is dark matter really made of? That question is not merely asking where it is, or how much there is, or what it does. It asks what kind of stuff could be so abundant, so influential, and yet so difficult to detect. For decades, scientists have proposed candidates. Some are heavy particles that barely interact with ordinary matter. Some are extremely light particles that may behave more like a field spread through space. Some ideas are simple and elegant. Others are strange enough to make even seasoned physicists pause and refill their tea. One family of ideas involves particles that interact through gravity, and perhaps through a very weak force, but not through electromagnetism. That would explain why they do not emit or absorb light. They would pass through ordinary matter almost unnoticed, not because they are ghosts in a supernatural sense, but because the usual ways particles bump, scatter, and glow would barely apply. Right now, as you listen, dark matter particles, if they are particles of that kind, may be passing through Earth, through buildings, through mountains, through you, with almost no chance of striking anything. A cosmic drizzle so subtle that we do not feel a drop. That thought can sound unsettling at first, but it's not harmful in the ordinary sense. Neutrinos, known particles produced by the sun and other processes, already pass through us constantly, also interacting very rarely. The universe is full of things moving through things. Most of matter is empty space at the atomic level, and many particles are not sociable. Dark matter, if it is particle-based, may simply be one of the least sociable ingredients in the cosmic recipe. Another possibility is that dark matter is made of particles called axions, or something like them. These would be very light and would have been produced in the early universe. Instead of behaving like little cosmic billiard balls, they might form a more wave-like background. The details are still uncertain, and scientists are searching in many ways. Some experiments sit deep underground, shielded from ordinary radiation, waiting for the faintest possible signal. Others use powerful magnets, delicate detectors, or astronomical observations to look for hints. It is a patient kind of hunting. Not dramatic in the sense of chasing a beast through the forest, but dramatic in the way a library can be dramatic if somewhere inside it is a book that explains the universe, and no one knows which shelf it is on. There have also been ideas that dark matter might not be new particles at all, but ordinary objects that are simply hard to see. Perhaps faint stars, dead stars, rogue planets, black holes, or other compact bodies. Some of these objects certainly exist, and some may contribute a little to the unseen mass. But evidence suggests they cannot account for all of dark matter. There are not enough of them in the right places, and certain observations rule out large populations of many such objects. The mystery cannot be solved simply by saying there are lots of dim things hiding between the bright ones. Nature, as usual, is not giving away the ending that easily. Then there is the more radical thought. Maybe dark matter is not matter at all. Maybe our understanding of gravity is incomplete. Perhaps on the scale of galaxies, gravity behaves differently from what we expect. This idea has been explored seriously. It is not foolish to question gravity, especially when history has already shown that Newtonian gravity, brilliant as it was, needed Einstein to deepen it. Modified gravity theories can explain some galaxy rotation patterns surprisingly well, but they struggle with other evidence, especially the behaviour of galaxy clusters, the cosmic microwave background, and the way large-scale structure formed. Many scientists still consider dark matter the stronger explanation, but the debate remains part of the story. A good mystery should allow more than one suspect for a while. The reason dark matter is so compelling is that it solves many different puzzles at once. It helps explain galaxy rotation. It helps explain clusters. It helps explain gravitational lensing. It fits with patterns seen in the oldest light in the universe, the afterglow from the early cosmos. It helps explain how galaxies formed and how the cosmic web grew. When one idea quietly connects many observations, scientists pay attention. It does not mean the case is closed. It means the trail is strong. Yet the missing piece is still enormous. We have not directly detected the dark matter particle, if a particle is what it is. We have not held it in a detector and said, "There you are." We have not watched it interact in a laboratory in a way that removes all doubt. The evidence is gravitational, indirect and powerful, but the substance itself remains unknown. That is why the question feels so alive. Dark matter is not a dusty old topic stored away in textbooks. It is active, unresolved, and central to modern physics. There is something very human about this. We know dark matter by relationship rather than appearance. We know it by what it does to others. It changes the speed of stars. It bends distant light. It gathers galaxies into clusters. It shapes the vast web of the cosmos. It is like understanding the wind by watching trees move, or understanding a person in another room by hearing the floorboards creak. The cause is hidden, but its presence is written in motion. And perhaps that is a fitting way to begin. The universe is not only what shines, it is also what holds the shining things together. It is the visible and the invisible, the measured and the inferred, the bright lanterns and the dark framework around them. When we ask what dark matter is made of, we're really asking what kind of hidden material helped build the cosmic home we live in. We're asking why galaxies have the shapes they do, why stars remain in their grand, slow orbits, why the universe formed its enormous patterns instead of remaining smooth and featureless. Tonight, we will take this question gently. There is no need to rush after something that has avoided capture for billions of years. We will follow the clues the way astronomers did, beginning not with particle detectors or exotic theories, but with galaxies themselves. Because the first great hint was not found in a laboratory. It was found in the sky, in the motion of stars and galaxies that seemed to be moving under the influence of something unseen. Picture again that spiral galaxy, turning in silence. Its outer stars continue their wide, slow paths, not drifting away, not obeying the expectations of visible matter alone. Around it, beyond the glowing arms, beyond the dust lanes and the star-forming clouds, stretches an invisible halo. We cannot photograph it directly. We cannot make it glow. But without it, the galaxy would not move the way it does. The stars are telling us something. They have been telling us for a long time. All we had to do was learn how to listen. At first, the missing matter did not announce itself with a single dramatic discovery. There was no one night when an astronomer looked through a telescope, spilled their tea, and declared that most of the universe had vanished. Science is usually quieter than that. It is more often a slow gathering of awkward facts, a set of measurements that do not quite fit, a suspicion that grows in the corner of the room until everyone has to stop pretending it is only the furniture creaking. The earliest clues came from galaxies, those great cities of stars scattered through the dark. To the eye, a galaxy can seem complete. A spiral galaxy especially looks like a finished object, with its bright centre, curved arms, glowing gas clouds, and thin lanes of dust. It feels natural to assume that what shines is what matters most. After all, stars are heavy. Gas is real. Dust is there too, even if it is easier to notice when it blocks something behind it. If you want to understand the mass of a galaxy, surely you should count the stars, add the gas, make a careful estimate of the faint material, and then let gravity do the rest. For a while, that seemed reasonable. Astronomers had already learned that galaxies were not little clouds inside our own Milky Way, but separate systems far beyond it. That realization alone had expanded the known universe from a single island of stars to an ocean of islands. The Milky Way was no longer the whole stage. It was one galaxy among many, and each galaxy carried its own population of stars, its own history, its own slow-turning motion. Once astronomers began treating galaxies as physical systems, not just pretty smudges in telescopes, they wanted to know how they moved, how much they weighed, and what held them together. Measuring the weight of a galaxy is not like placing it on a scale, though if someone ever invents a scale large enough, it will need a very sturdy kitchen counter. Instead, astronomers infer mass by studying motion. Gravity controls the way objects move. If stars are orbiting a galactic center, their speed carries information about how much mass is pulling on them. The more mass there is inside their orbit, the stronger the pull must be to keep them moving along curved paths. This is the same general idea that lets astronomers estimate the mass of the Sun by watching planets move around it. Motion becomes a kind of confession. The objects do not speak, but their paths tell the truth. In the bright inner parts of many spiral galaxies, the stars and gas move quickly, as expected. There is plenty of visible matter there. The central regions are crowded with stars, gas clouds, and dust. But as astronomers measured farther outward, into the dimmer edges of galactic disks, something surprising appeared. The outer material was moving too fast. Not just a little too fast in one galaxy, and not only in a measurement that could be politely blamed on tired equipment. Again and again, stars and gas far from the centre moved as though the galaxy contained much more mass than could be seen. If most of the mass were concentrated in the bright central region, the outer stars should have moved more slowly. That would have made intuitive sense. In our solar system, the inner planets move faster than the outer planets, because most of the mass is concentrated in the Sun. Mercury hurries around close to the Sun, while Neptune takes its long, slow route far away. If a spiral galaxy were built mostly from its visible stars, astronomers expected a similar pattern in broad terms. The farther out you went, the more the orbital speeds should decline. But galaxies did not behave so politely. The speeds often stayed nearly flat. The outer stars and gas kept moving at high speeds, as if the visible disk were only part of a much larger mass distribution. The stars were acting like they were embedded in something broad and invisible, something extending beyond the luminous edge of the galaxy. The galaxy did not end where the starlight faded. Gravity continued outward, quietly and insistently. This was not the first time missing mass had troubled astronomers. Earlier in the 20th century, a Swiss astronomer named Fritz Zwicky studied a large cluster of galaxies called the Coma Cluster. It is a vast gathering of galaxies bound together by gravity, or at least it appeared to be bound. Zwicky measured how fast the galaxies in the cluster were moving. What he found was deeply strange. The galaxies were moving so quickly that, based on the visible matter alone, the cluster should not have held together. They should have escaped, flying apart like sparks from a fire. Yet the cluster remained a cluster. Zwicky concluded that there must be a great deal of unseen matter providing extra gravity. He used a phrase that translates as dark matter. It was a bold idea, and in some ways it was ahead of its time. But the astronomical community did not immediately gather around it with warm blankets and applause. Zwicky had a reputation for being brilliant but difficult, and his claim was hard to verify with the tools available then. The measurements were challenging. The uncertainties were large. The idea lingered, important but not yet decisive, like a note pinned to the universe that few people were ready to read closely. The stronger wave of evidence came later, especially through the careful work of astronomers studying spiral galaxies. Among the most important figures was Vera Rubin, whose observations helped transform dark matter from a strange possibility into a central problem of modern astronomy. Rubin, working with instrument maker Kent Ford and others, measured the motion of stars and gas in galaxies with great precision. She studied how galaxies rotated, not only in their bright centres, but across their extended disks. This work required patience. Telescopes do not simply hand over answers because one has asked nicely. Astronomers collect light, spread it into its colours, and examine subtle shifts that reveal motion. Light from material moving toward us is shifted one way. Light from material moving away is shifted another. From these shifts, scientists can infer how fast different parts of a galaxy are rotating. It is a delicate method, but it is powerful. The galaxy leaves a motion signature in its light. Rubin and her colleagues found that the outer regions of spiral galaxies were not slowing down as expected. The rotation curves stayed flat. That phrase sounds dry, almost like something found in the back of a technical report, but it carries enormous meaning. A rotation curve is simply a description of how orbital speed changes with distance from a galaxy centre. If visible matter were enough, the curve should have dropped in the outskirts. Instead, it often remained level. The outer galaxy was moving as if mass continued to be present far beyond the visible stars. This was not one odd galaxy being difficult before breakfast. It was a pattern. Galaxy after galaxy told the same story. The visible matter could not account for the observed motion. Something was missing, or something about gravity itself was not being understood. The evidence did not yet reveal what the hidden component was, but it made the problem harder to ignore. One of the reasons Rubin's work was so powerful is that it was clear, repeated, and direct in its implications. A single strange measurement can be exciting, but also fragile. Instruments can misbehave, assumptions can be wrong, a galaxy can be unusual. But when many galaxies, measured carefully, show the same kind of mismatch, the mystery becomes sturdier. It begins to look less like a mistake and more like a feature of the universe. There is a gentle irony here. Dark matter became convincing partly because ordinary galaxies were too well behaved. The outer stars did not scatter away. The disks remained coherent. Spirals kept their shapes. The motion was not chaos. It was orderly motion under extra gravity. The problem was not that galaxies looked broken. The problem was that they looked stable when, according to the visible matter alone, they should have been far less stable. To picture the issue, imagine watching dancers move in a dark ballroom. You can see a few of them under a dim chandelier in the centre, but most of the room is shadowed. The visible dancers move in circles, and at first you assume they are guiding the whole dance. Then you notice that dancers near the edge, barely visible in the dark, are moving as though they are being led by partners you cannot see. Their steps are too controlled, too coordinated, too fast for the few visible people in the centre to explain. The natural conclusion is not that the outer dancers have forgotten the rules, but that there are unseen partners shaping the movement. Galaxies are not ballrooms, of course. They do not wear shoes, and if they did, the laces would be several thousand light-years long, but the point holds. Motion can reveal hidden influence. Another important clue came from the gas in galaxies, especially hydrogen gas that extends beyond the bright visible disk. Stars fade at the edges, but gas can stretch farther out. Radio telescopes can detect signals from this cold hydrogen, allowing astronomers to trace rotation well beyond the regions that optical telescopes show brightly. The gas became a test particle, a quiet marker of gravitational influence in the outskirts. It too moved too quickly. The invisible mass was not merely affecting the star-filled regions, its influence extended into the dark outskirts where the galaxy looked thin and faint. This helped shape the idea of the dark matter halo. A galaxy, in this view, sits inside a large, roughly spherical region of dark matter. The visible disk is embedded within it, like a bright coin inside a much larger transparent sphere. The halo does not shine, but its gravity dominates the outer regions. It changes how stars and gas move. It can extend far beyond the visible boundaries of the galaxy. The word halo sounds almost angelic, which is perhaps misleading, because this halo is not made of light. It is an invisible gravitational envelope. The Milky Way has such a halo too, according to the evidence. Our own galaxy is not exempt from the mystery. We live inside the problem. The Sun orbits the centre of the Milky Way, along with the rest of the galactic disk, and the motion of stars around us is influenced by the mass of the galaxy, visible and invisible. When astronomers study the Milky Way's rotation, the motions of satellite galaxies, and the behaviour of stellar streams, they infer a large dark matter halo surrounding us. We are not looking at dark matter from the outside only. We are inside one of its structures, moving through it as Earth moves around the Sun, and the Sun moves through the galaxy. That thought is easy to miss because dark matter does not feel local. It sounds like something far away, something belonging to huge cosmic maps and distant galaxy clusters. But if the standard picture is correct, dark matter is present here too, passing through the solar system, through Earth, and through every quiet room where someone is trying to fall asleep to astronomy. It does not gather into planets or furniture, because it does not interact with ordinary matter in the way atoms do. It does not make dark rocks or dark raindrops. It remains diffuse, spread through space, contributing gravity without becoming part of ordinary chemistry. That is one reason the galaxy evidence was so important. It showed that whatever dark matter is, it behaves differently from ordinary matter. Ordinary matter radiates energy. Gas clouds can cool, collapse, and form stars. Dust absorbs and emits light. Atoms interact through forces that let them collide, stick, heat up, and settle into disks. Dark matter does not seem to do this much, if at all. It forms extended halos rather than thin, glowing disks. It provides gravity, but does not join the visible dance in the usual way. This difference is a clue to its nature. Still, astronomers had to be careful. Could the missing mass be ordinary matter that simply failed to shine? Perhaps galaxies were filled with faint red stars, cold gas, dead stellar remnants, or wandering planets. These objects would be difficult to see and could add mass. The idea was reasonable enough to investigate. Scientists looked for such hidden, ordinary matter in many forms. They studied faint stars. They searched for compact objects by watching whether they briefly magnified background stars as they passed in front. They measured gas and dust. They considered black holes, brown dwarfs, and all sorts of dim possibilities. Some unseen ordinary matter certainly exists. Space is not tidy. There are faint stars, cold clouds, stellar remnants, and objects too dim to notice easily. But the evidence showed that these ordinary dark objects could not make up all the missing mass. There were not enough of them, and the broader cosmological evidence did not allow ordinary matter to dominate in that way. The missing component had to be something else, something not made of the familiar atoms that build stars, planets, oceans, and tea biscuits. The galaxy evidence also became stronger when combined with observations from clusters and gravitational lensing. In clusters, astronomers could compare where the visible matter was with where the gravity appeared to be. In some spectacular cases, such as colliding galaxy clusters, the ordinary matter and the gravitational mass appear separated. Hot gas, which makes up much of the ordinary matter in clusters, can collide and slow down during a cluster collision. Dark matter, if it barely interacts except through gravity, would pass through more easily. Lensing maps can then show gravitational mass located away from the hot gas. These cases provide powerful evidence that the missing gravity is not just a misunderstanding of visible matter, it behaves like an additional component. But even without those later pieces, galaxies themselves had already opened the door. Their rotation was a persistent message. Something unseen was contributing mass. The stars in the outskirts were not merely moving too fast, they were revealing the presence of an invisible structure wrapped around the galaxy. There is something almost humble about how this discovery unfolded. The universe did not reveal dark matter by showing us dark matter. It revealed it by letting visible matter misbehave in a consistent way. The stars became witnesses. The gas became testimony. The galaxies, turning slowly across unimaginable spans of time, became instruments. This is often how astronomy works. We cannot travel to a distant galaxy and place sensors along its spiral arms. We cannot scoop up a piece of its halo and carry it back to a laboratory. We receive light, measure motion, compare patterns, and ask what must be true for the observations to make sense. It is detective work performed across cosmic distances, with the evidence arriving as photons that may have travelled for millions of years before touching a mirror on Earth. And yet, from such faint signals, a profound conclusion emerged. Galaxy is not made only of what they show us. The bright disk is only part of the story. The graceful spiral arms, the glowing nebulae, the star clusters, the dust lanes, all of that is real and beautiful. But it's not enough to explain the galaxy's own movement. Around and through it is a larger gravitational presence. It does not decorate the galaxy, it governs it. This shifted the way astronomers thought about galaxies. A galaxy was no longer simply a collection of stars and gas held together by their own visible mass. It was a luminous system embedded in a dark halo. The halo became central to explaining how galaxies form, how they grow, how they merge, and how they remain stable. In modern simulations of cosmic history, dark matter halos form first, gathering under gravity, merging into larger structures, creating the wells into which ordinary matter falls. Gas then cools inside these wells, forming stars and disks. The visible galaxy becomes, in a sense, the glowing outcome of an invisible beginning. That idea changes the emotional picture too. We often imagine darkness as emptiness, but in cosmology, darkness can be structure. The dark regions around galaxies are not necessarily vacant. They may be full of matter that does not shine. The night between stars is not simply a blank background. It can contain the mass that shapes the stars themselves. It is a reminder that visibility and importance are not the same thing. Even the word missing can be slightly misleading. The matter was missing from our inventories, not from the universe. The galaxies knew it was there. Their stars had always moved under its influence. Their gas had always traced its pull. It was missing only from the human account, from the list we had made by looking for light. The universe was not lacking matter. We were lacking a way to see it. As the evidence mounted, dark matter became not just an explanation for galaxy rotation, but a doorway into a larger cosmic story. If galaxies sit in dark halos, then groups and clusters must sit in even larger dark structures. If halos merge, then the universe's great web of galaxies may trace an underlying web of dark matter. The luminous universe may be like frost forming along invisible branches, revealing the shape of something colder and hidden underneath. This connection between galaxies and the cosmic web would become one of the most important developments in understanding dark matter. The same invisible substance that helps hold a spiral galaxy together also appears to guide the arrangement of galaxies across hundreds of millions of light years. The small mystery of a star moving too fast at the edge of a galaxy leads naturally to the enormous mystery of why the universe has the structure it does. But before we move outward to the largest patterns, it is worth lingering with the galaxies a little longer. They are still among the clearest guides we have. Every spiral galaxy with a measured rotation curve is a kind of quiet argument. Every dwarf galaxy with motions too energetic for its visible stars adds another line to the case. Dwarf galaxies are especially interesting because they can be dominated by dark matter. Some contain relatively few stars but behave as though they're held by far more mass than the stars provide. They are faint little lanterns inside large invisible wells. In them, the imbalance between visible and hidden matter can be extreme. This makes dwarf galaxies valuable but challenging laboratories. They are dim, delicate, and often affected by their larger neighbours. Still, they help astronomers test dark matter models. If dark matter is made of certain kinds of particles, it should produce certain patterns in small galaxies. If it behaves slightly differently, perhaps warmer, lighter, or more self-interacting than expected, the smallest galaxies may reveal the difference. The outskirts of the cosmos, the faintest systems, the barely visible companions of great galaxies, may carry clues that the bright grand spirals cannot. That is another gentle lesson from this subject. The faint things matter. The small things matter. A dim dwarf galaxy can challenge a theory. A tiny shift in starlight can reveal motion. A faint distortion in a background image can map invisible mass. Astronomy trains patience into perception. It asks us not only to admire what is bright, but to pay attention to what is slight, indirect, and easy to overlook. The story of how galaxies revealed missing matter is therefore not just a story about mass, it is a story about changing what counts as evidence. For centuries, astronomy was tied closely to sight. The telescope extended the eye. It gathered more light than the eye could gather alone, but modern astronomy goes beyond seeing. It measures spectra, motion, radio signals, X-rays, gravitational bending, and patterns in ancient radiation. Dark matter forced astronomers to trust gravity as a kind of vision. If light would not show the hidden mass, motion would. And motion spoke clearly. The outer stars moved too quickly. Galaxy clusters held together too strongly. Gas traced deep gravitational wells. Light bent around invisible mass. The same message appeared in different languages. Something unseen was there. Not just somewhere, everywhere that galaxies told the tale. This is why dark matter is such a compelling mystery. It is not a decorative idea added to make the universe more dramatic. It is a response to evidence. Remove dark matter from our models, and galaxies become difficult to explain. Clusters become difficult. The growth of structure becomes difficult. The universe starts leaving too many receipts for mass we have not paid attention to. Of course, saying that galaxies revealed something missing is not the same as saying they revealed what it is. That remains the deeper question. The galaxies showed us the outline of the invisible. They showed us the gravitational footprint. But a footprint is not a face. The next challenge is to understand the larger structure dark matter creates, how it gathers, how it threads through space, and how visible galaxies appear to form along its hidden framework. The spiral galaxy we imagined earlier is still turning. Its stars continue their long orbits. Its outer gas moves with surprising speed. Around it, the halo remains unseen, not glowing, not cooling into stars, not introducing itself directly. Yet the galaxy's motion keeps pointing toward it, patiently, the way a compass points north whether or not anyone is watching. The more carefully astronomers listened, the clearer the message became. The universe had more gravity than light could explain, and galaxies were the first great witnesses willing to tell us so. Now that galaxies have quietly given away the presence of something unseen, it helps to pull the view farther back. Not just a little farther, as if we were leaving one spiral galaxy behind and drifting toward another, but much farther, until whole galaxies become points of light, then clusters become small gatherings, and the universe begins to show its largest pattern. At that scale, the cosmos does not look evenly sprinkled with galaxies, like sugar spread smoothly across a table. It looks more like a vast network. Galaxies gather along long threads. Clusters sit where those threads meet. Between them are enormous empty regions, great cosmic voids where very few galaxies live. The universe, when mapped across hundreds of millions of light years, has a texture. It has strands, knots, sheets, and hollows. Astronomers call this structure the cosmic web, and the name is unusually good. It really does resemble a web, though one spun not by anything alive, but by gravity working patiently for billions of years. It is not a web you could touch, and it is not made from a single material stretched across space. It is a pattern of matter, visible and invisible, shaped by tiny differences in density that were present when the universe was young. Where the early universe was slightly denser, gravity pulled in more matter. Where it was slightly less dense, matter slowly drained away into the growing regions around it. Over immense stretches of time, those small differences became the grand architecture of the cosmos. Dark matter is central to this story. If galaxies revealed that something missing was holding them together, the cosmic web suggests that the same missing something helped build the universe on its larger scales. It is not merely a hidden ingredient inside galaxies. It is the underlying structure, the gravitational skeleton on which visible matter gathered. The stars, gas, galaxies, and clusters we can see are like lights along a vast invisible framework. They show us where the framework is thickest, but they are not the whole framework themselves. To imagine this, picture a city at night seen from high above. The brightest streets and intersections reveal where people live and travel. Highways glow in long ribbons. Downtown areas burn with concentrated light. Suburbs form dimmer branching patterns. But the lights are not the city's foundation. They trace roads, buildings, and human activity that already exist. In a similar way, galaxies trace something larger. They mark the places where matter has collected most strongly. They illuminate the densest ridges and nodes of a dark structure that extends far beyond the parts we see. This is why the idea of dark matter as a skeleton is useful. A skeleton gives shape without being the most visible feature. We do not usually look at a person and see bones first. We see the face, the movement, the surface, the expression. But the skeleton supports the whole form. It determines posture, structure, and strength. In the universe, dark matter seems to play a comparable role. Ordinary matter provides the glowing face of the cosmos. Dark matter gives much of the underlying gravitational shape. The story begins very early, long before galaxies existed. The young universe was hot, dense, and filled with radiation and particles. It was not perfectly smooth. It had tiny variations, small differences in density from one region to another. These differences were incredibly slight, but they mattered. Gravity is patient and easily encouraged. Give it a region that is just a little denser than average, and it will begin pulling in more material. The more it pulls in, the stronger its gravity becomes. The stronger it becomes, the more it pulls in. Given enough time, small irregularities can grow into enormous structures. Ordinary matter, the kind made of atoms, had a difficult time clumping at first because it was strongly linked with light in the early universe. Radiation pushed on it, scattered from it, and kept it from collapsing freely. Dark matter, by contrast, appears not to interact with light in that way. It could begin gathering under gravity without being shoved around as strongly by radiation. This gave it a head start. It formed gravitational wells, invisible regions where matter was slightly more concentrated. Later, when the universe cooled enough for ordinary matter to move more freely, gas could fall into these wells. Over time, that gas cooled further, collapsed, and formed the first stars and galaxies. This makes dark matter feel less like an extra piece added after the visible universe was built, and more like the early frame around which the visible universe assembled. Before the stars lit up, before spiral arms formed, before galaxies took on the shapes we admire in telescope images, dark matter was already helping organize where matter would go. It was the quiet builder working before dawn. Computer simulations have become one of the main ways scientists explore this process. Researchers create models of the early universe with tiny density variations, then let gravity act over cosmic time. When dark matter is included, these simulations naturally produce structures that resemble the cosmic web we observe. Dense clumps form first, then merge into larger halos. Filaments stretch between them. Voids expand as matter flows away from under dense regions. Galaxies form within dark matter halos, especially where gas can cool and become dense enough to make stars. The result looks remarkably like the large-scale maps of galaxies that astronomers have produced. This agreement is one of the reasons dark matter is so deeply woven into modern cosmology. It does not merely explain one strange fact, It helps explain the shape of the universe itself. Galaxy rotation curves were one clue, galaxy clusters were another, but the cosmic web is a clue written across the largest scales we can map. The universe has a pattern, and dark matter helps explain how that pattern grew. The cosmic web is not just a poetic image from a telescope poster. It is something astronomers can map. Large galaxy surveys measure the positions and distances of millions of galaxies, building three-dimensional maps of where galaxies sit in space. These maps show long chains and sheets of galaxies surrounding empty voids. The pattern is not random. It has the signature of gravitational growth. The galaxies are gathered where the underlying matter distribution is densest. Since most of that matter appears to be dark, visible galaxies are acting as tracers, like leaves caught along the surface of a river current showing the flow beneath. There is a small complication here, as there often is in science, because galaxies do not trace dark matter perfectly. Ordinary matter has its own behaviour. Gas can cool, heat, form stars, explode from supernovae, fall into black holes, and be blown outward by energetic processes. Galaxies are shaped by messy astrophysics, not only by gravity. So when astronomers use galaxies to infer the dark matter web, they have to be careful. The lights do not reveal the skeleton with perfect accuracy. Still, on large enough scales, the pattern is clear. Galaxies are not scattered at random. They follow the deep gravitational architecture. Another way to study the dark matter skeleton is through gravitational lensing. As light from distant galaxies travels toward us, it passes through the uneven mass distribution of the universe. The dark matter along the way bends that light very slightly. In many cases, the effect is too small to notice in a single galaxy image. But when astronomers study huge numbers of galaxies statistically, the tiny distortions add up. This technique can map the mass distribution directly, including matter that emits no light. It is one of the closest things we have to seeing dark matter, though what we actually see is the way it bends the images of background galaxies. These lensing maps reveal a web-like distribution of mass that lines up with the visible cosmic web. The places where galaxies cluster tend to be places where the total mass is high. The filaments of visible galaxies trace filaments of invisible matter. The nodes, where clusters sit, are massive knots in the web. This gives us a second kind of evidence. It is not only that galaxies are arranged in a web, the gravity itself is arranged that way too. The voids are just as important as the filaments. A void is not completely empty, but it is much emptier than average. These regions can span tens or hundreds of millions of light years. They are the great quiet rooms of the universe, containing relatively few galaxies. Matter has flowed away from them over time toward denser regions. If the cosmic web is a structure of strands and knots, the voids are the spaces between them. They are not mistakes or blank spots. They are part of the architecture. Their size and distribution help scientists test models of cosmic evolution. Dark matter affects voids as well. In a universe with different kinds of dark matter, the structure of voids, filaments, and small galaxies could change. If dark matter moved too quickly in the early universe, it would smooth out small structures, making fewer small halos. If it interacted strongly with itself, halos might look different. If it were extremely light and wave-like, small-scale structure might be altered in subtle ways. This is why the cosmic web is not only evidence that dark matter exists, but also a possible clue to what dark matter is made of. Its fingerprints may be hidden in the details of structure. The ordinary matter that becomes gas and stars does not simply fall into dark matter halos in a neat and tidy way. It flows along filaments. In modern simulations, galaxies are fed by streams of gas that travel through the cosmic web. Clusters grow where filaments meet. The largest galaxies often live in these dense nodes, where mergers are more common, and gas has had long histories of heating and cooling. Smaller galaxies form along thinner strands or in smaller halos. In this picture, galaxies are not isolated islands scattered across emptiness. They are part of a cosmic ecosystem connected by long gravitational channels. This changes the way we think about the Milky Way too. Our galaxy is not floating alone in a featureless dark sea. It belongs to a small group of galaxies, including the Andromeda Galaxy and many smaller companions. That group exists within a larger regional structure, influenced by nearby clusters, filaments, and voids. The Milky Way is part of the cosmic web, a single glowing settlement on a vast dark framework. Our night sky may feel local and intimate, but the galaxy itself is embedded in a much larger environment. One of the great achievements of cosmology has been connecting these different scales. The motion of stars in a galaxy, the behavior of galaxies and clusters, the bending of light, the pattern of ancient radiation, and the arrangement of galaxies across the universe all point toward the same broad picture. Dark matter forms halos and filaments. Ordinary matter falls into the densest regions. Stars light up where gas cools. Galaxies become visible markers of a deeper structure. The oldest light in the universe adds another piece to this story. This light comes from a time when the universe first became transparent. Before that, light scattered constantly from charged particles and could not travel freely. After the universe cooled enough for atoms to form, light was released and has been travelling ever since, stretched by cosmic expansion into a faint microwave glow. It carries a snapshot of the early universe, including the tiny density variations that would eventually grow into galaxies in the cosmic web. When scientists study this ancient light, they find patterns that match a universe containing ordinary matter, dark matter, and dark energy in particular proportions. The exact details are technical, but the important point is simple enough. The early universe already carried the seeds of structure, and the growth of those seeds into the cosmic web works very well when dark matter is included. Without dark matter, the universe would struggle to form the structures we observe by the time we observe them. Gravity from ordinary matter alone would not have had the same head start. This is a powerful idea. When we look at a galaxy cluster today, we're seeing the result of billions of years of gravitational growth from tiny early fluctuations. The cluster is not just a pile of galaxies, it is the mature form of a density enhancement that began in the hot young universe. Dark matter helped that enhancement grow. The web we see today is ancient in origin, shaped over cosmic time. There is a quiet steadiness in this process. Gravity is not dramatic moment by moment. It does not rush. It works continuously. It gathers, amplifies, draws matter inward, and empties the voids. Over billions of years, tiny differences become vast patterns. The cosmic web is the universe's long memory of its earliest unevenness. Dark matter halos are the basic building blocks in this structure. A halo is a region where dark matter has gathered and become gravitationally bound. Small halos form, merge, and become larger halos. Within them, ordinary matter may form galaxies if conditions allow. Not every halo hosts a bright galaxy. Some may be too small or too poor in gas to form many stars. Others may have lost gas due to radiation or explosions. This means the dark matter skeleton may contain many more structures than the visible galaxy population reveals. There may be dark halos with little or no starlight, invisible clumps in the cosmic framework. This possibility is important because it offers another way to test dark matter. If the standard picture is correct, there should be many small dark matter halos. Some may host faint dwarf galaxies. Some may be nearly invisible. Astronomers look for their effects through gravitational lensing, through disturbances in streams of stars around galaxies, and through the motions of visible companions. The small-scale structure of the dark matter web may tell us whether dark matter is cold, warm, self-interacting, wave-like, or something else entirely. Cold dark matter is the simplest and most successful version in many models. The word cold here does not mean chilly in the everyday sense, like a forgotten cup of tea. It means the dark matter particles moved relatively slowly in the early universe compared with the speed of light, allowing small structures to form efficiently. This model produces a rich hierarchy of halos, from small to enormous. It matches many large-scale observations very well. But there are still debates and puzzles on smaller scales. Some simulations predict more small halos than the number of observed dwarf galaxies. Some dark matter density profiles in simulations seem different from what certain galaxies suggest. These issues may be due to complex ordinary matter physics, or they may hint at something deeper about dark matter itself. Here the story becomes careful rather than conclusive. It is tempting to say every mismatch means dark matter theory is in trouble, but ordinary matter can be surprisingly disruptive. Star formation, supernova explosions, gas flows, and black hole activity can reshape galaxies and alter the distribution of matter in their centers. Small galaxies are especially vulnerable. A few bursts of star formation can move gas around and change the gravitational environment. So scientists must separate what dark matter predicts from what ordinary astrophysical processes modify. This is not easy. The universe has not arranged itself for our convenience, which is inconsiderate but consistent. Still, the large-scale success of the dark matter picture is striking. When simulations begin with early universe conditions and include dark matter, they form web-like structures resembling what galaxy surveys reveal. When lensing maps the mass distribution, it confirms that much of the web is invisible. When clusters are studied, their masses exceed the visible material. When galaxies rotate, their outer parts demand extended halos. These are not separate mysteries piled randomly on a desk, they connect. The cosmic web also helps explain why galaxies are not distributed evenly. In dense regions, galaxies interact more often. They merge, strip gas from one another, and evolve differently from galaxies in quieter environments. Clusters are crowded places, full of gravitational encounters and hot gas. Filaments are more like highways feeding clusters. Voids are comparatively isolated regions where galaxies are fewer and often evolve differently. Dark matter sets the stage for this environmental diversity. It determines where matter gathers most strongly and where emptiness grows. This means that dark matter has influenced not only galaxy positions, but galaxy histories. A galaxy's life is shaped by the halo it lives in, the larger structure around it, the filaments that feed it, and the neighbours it meets. The stars inside a galaxy tell one story. The dark matter environment tells another, larger one. To understand a galaxy fully, astronomers must understand both. In a way, this is similar to understanding a tree. You can study the leaves, bark, branches, and fruit, but you also need to understand the soil, water, light, and climate. A galaxy's visible stars are like leaves catching the light. Its dark matter halo is part of the soil and root system, unseen but essential. The cosmic web is the larger landscape in which many such trees grow. There is something soothing about the scale of it, even though it is enormous. The universe is not a meaningless scatter. It has structure. It grew from small beginnings. It contains patterns that can be studied, mapped, and understood, at least partly. Dark matter may be invisible, but it is not chaos. It behaves with gravity. It builds halos. It forms filaments. It gathers clusters. It helps the universe become organized enough for stars, planets, and eventually curious minds. The phrase dark matter skeleton should not make the cosmos feel cold or lifeless. A skeleton is not a dead thing in this metaphor. It is support. It is shape. It is the hidden architecture that allows luminous complexity to arise. Without it, the visible universe might be far smoother, poorer in galaxies, slower to form structure. The night sky above us, with its stars and distant galaxies, may owe much of its richness to something that never shines. That is one of the deeper lessons of dark matter. The visible universe depends on the invisible. The bright things are guided by the dark. The galaxies that fill telescope images are not independent ornaments pasted onto empty space. They are the glowing parts of a much larger cosmic body. As scientists continue mapping the cosmic web, They are also looking for signs that reveal the nature of the dark matter itself. The arrangement of small galaxies, the density of halo centers, the shapes of lensing patterns, the distribution of matter in voids, the behavior of colliding clusters, all of these may contain clues. Dark matter may not speak through light, but it speaks through structure. The web is its handwriting across the universe. The challenge is learning to read that handwriting without mistaking the flourishes of ordinary matter for the letters of dark matter. Gas can be heated, stars can explode, black holes can launch energy into their surroundings, galaxies can collide and stir everything around them. The visible universe is noisy. Dark matter is quieter, but its effects are broad and deep. By comparing many observations across many scales, scientists slowly separate the signal from the complications. This is why dark matter research feels like listening for a low note beneath a symphony. The violins and trumpets of ordinary matter are easier to hear. Stars blaze, gas glows, galaxies collide in spectacular shapes, but underneath is a baseline, steady and gravitational, setting the rhythm for the whole performance. You may not notice it at first, but remove it, and the music changes completely. The cosmic web is that baseline made visible through galaxies. It is the large-scale result of dark matter gathering and ordinary matter following. It tells us that the missing mass is not merely hidden in the outskirts of galaxies, but woven throughout the universe. It tells us that dark matter is not a local patch for a local problem. It is a cosmic ingredient. And so the view widens. The same unseen influence that kept outer stars moving too quickly also stretched itself into filaments between clusters. The same gravitational pull that wrapped galaxies in halos also helped carve out voids. The same hidden matter that revealed itself through rotation curves now appears as the scaffolding of the universe's grandest pattern. From here, the question becomes even more focused. If dark matter built this skeleton, what kind of material could do such a thing while remaining invisible, diffuse, and mostly untouched by light? It must gather under gravity, but not collapse into bright stars. It must shape galaxies, but not behave like ordinary gas. It must be abundant, stable, and quiet. These requirements narrow the field, but they do not yet give a final answer. The cosmic web shows us the scale of the mystery. It is not a small missing piece tucked behind a galaxy's glowing edge. It is a universe-wide framework stretching from the faintest dwarf galaxies to the largest clusters, from the early ripples of the young cosmos to the present structure of space. The galaxies are lanterns along its strands, the clusters are bright knots in its joints, the voids are the deep spaces between its ribs, and through it all, dark matter remains unseen, not absent, but quietly holding the shape of everything we can see. Once the universe begins to look less like a scatter of lonely galaxies and more like a vast structure built around something invisible, the next question becomes difficult to avoid. If dark matter is there, if it wraps galaxies in halos, if it gathers clusters, if it forms the hidden framework of the cosmic web, then what is it actually made of? Not what does it do, not where does it seem to be, but what is the stuff itself? What kind of matter can shape the universe so strongly, and yet pass through light as if light were not worth acknowledging at all? This is where the mystery changes character. Until now, dark matter has been a gravitational clue. It has been the extra pull in galaxy rotation, the missing mass in clusters, the skeleton beneath the cosmic web. But when we ask what it is made of, we step into a stranger room. The evidence tells us that something is there, but the list of possible identities is long, odd, and in some cases rather shy. The suspects range from dim, ordinary objects to exotic particles, from ancient black holes to faint fields spread through space, from things that may drift through your body unnoticed to possibilities that would require a deep change in how we understand nature. A good detective does not begin by choosing the most dramatic suspect. A good detective begins by asking what the culprit must be able to do. Dark matter must have mass, because it produces gravity. It must not give off much light or absorb much light because telescopes do not see it directly. It must be stable, or at least long-lived enough to remain present across the age of the universe. It must be abundant because the missing gravitational effect is not small. It must gather into halos around galaxies and into the larger web of structure, but it must not behave like ordinary gas, because ordinary gas cools, collapses, forms stars, and lights up. Dark matter seems to gather gravitationally while staying diffuse, quiet, and largely invisible. That is a surprisingly demanding job description. It rules out many familiar things. It cannot simply be dust. Dust blocks and reddens starlight, and astronomers are quite good at noticing it. It cannot simply be cold gas in the usual sense, because gas emits or absorbs radiation in ways we can detect, and it also behaves differently from the broad halos inferred around galaxies. It cannot simply be ordinary faint stars because there are not enough of them, and because even very dim stars leave traces. It cannot just be planets wandering between stars, although such planets may exist, because the numbers required would be enormous and inconsistent with other evidence. The universe is allowed to hide a few things in the attic, but dark matter is more like discovering that the attic is larger than the entire house. Still, ordinary dark objects were a natural place to look first. Scientists considered whether the missing mass might be made of objects that do not shine brightly. These could include brown dwarfs, which are sometimes called failed stars because they are not massive enough to sustain the long-lasting nuclear burning that makes stars shine steadily. They could include faint red stars, old white dwarfs, neutron stars, black holes, and rogue planets drifting through space without a parent star. In a broad sense, these are all ordinary matter. They are made from the same family of particles that make stars, planets, rocks, oceans, and people. They are dark only because they are dim, cold, compact, or difficult to see from far away. For a time, this seemed like a reasonable possibility. After all, the universe contains many things that are hard to observe. Not everything glows beautifully for our convenience. Brown dwarfs are faint. Old stellar remnants can be dim. Black holes do not emit light from within their event horizons. A galaxy could, in principle, contain many compact objects that add gravity while contributing little light. This idea had an appealing simplicity. Perhaps dark matter was not exotic at all. Perhaps it was just ordinary matter, hiding in forms we had underestimated. But observations made that explanation increasingly difficult. Astronomers searched for compact dark objects by looking for their gravitational effects on background stars. If a dark object passes in front of a more distant star, its gravity can briefly magnify the starlight, like a natural lens crossing the line of sight. These events are rare, but with enough monitoring they can reveal populations of hidden compact objects in galactic halos. The searchers found some such objects, but not nearly enough to explain all of dark matter. Other measurements also limited how much ordinary matter could exist without being seen. The early universe itself provides constraints, because the amounts of light elements formed shortly after the beginning depend on how much ordinary matter existed. Those clues tell us that ordinary matter cannot make up the missing mass in the required amount. This was a major turning point. Dark matter could not be explained simply by dim versions of familiar stuff. Some ordinary hidden objects exist, of course. The universe is full of faint leftovers and quiet wanderers, but they are not enough. The main component of dark matter must be something more unfamiliar, something outside the standard inventory of atoms. That idea sounds dramatic, but particle physics has already taught us that ordinary atoms are not the whole cast. Neutrinos, for example, are real particles that barely interact with matter. They stream from the sun, from exploding stars, from nuclear reactions, and from the early universe. Trillions of them pass through you every second without asking permission, and nearly all continue onward, as though your body were a faint mist. For a while, neutrinos seemed like natural dark matter candidates. They are real. They have mass, though extremely tiny mass. They are hard to detect. They do not shine. They are abundant. Unfortunately, ordinary neutrinos are not a good fit for the main dark matter. They move too quickly, especially in the early universe. If dark matter were mostly made of fast-moving particles like the neutrinos we know, it would smooth out small-scale structure. Galaxies and clusters would form differently from what we observe. The cosmic web would lose too much of its fine detail. So neutrinos contribute a little to the mass of the universe, but they cannot be the dominant dark matter. This shows how the identity of dark matter is constrained not only by whether a candidate is invisible, but by how it behaves over cosmic time. A candidate has to build the right kind of universe. It has to allow galaxies to form when they do, clusters to grow as they do, and small structures to survive in the numbers we see. It is not enough to be hard to detect. A good dark matter candidate must be cosmologically well behaved. That leads to a broad category of hypothetical particles that would be much less interactive than ordinary matter and much slower than ordinary neutrinos in the early universe. These particles would not feel electromagnetism, which means they would not emit, absorb, or reflect light. They might interact through gravity, and perhaps through other very weak processes. They would pass through ordinary matter almost all the time. They would gather into halos under gravity, but because they do not radiate energy efficiently, they would not cool and collapse into disks or stars. They would remain spread out in large, diffuse structures. This is why particle dark matter became so attractive. It naturally explains both invisibility and halo formation. Ordinary matter can radiate energy, lose heat, and settle into dense structures. That is why galaxies have thin disks, stars, and planets. Dark matter, if it cannot radiate in the same way, cannot easily shed energy. It remains puffier, forming broad halos. This matches what galaxies seem to require. It also fits the cosmic web, where dark matter gathers into large structures but does not glow. One famous class of candidates became known as weakly interacting massive particles. The phrase sounds a little clumsy, as if assembled by a committee that had already missed lunch. But the idea was elegant. These would be particles with substantial mass compared with many known particles, and with interactions far weaker than ordinary electromagnetic interactions. In the early universe, such particles could have been produced naturally. As the universe expanded and cooled, their abundance could settle into roughly the amount needed to explain dark matter. That coincidence made them especially appealing for decades. It felt as though particle physics and cosmology had quietly placed the same clue on the same table. These particles, if they exist, could be passing through Earth constantly. Very rarely, one might collide with an atomic nucleus in a detector, producing a tiny flash or vibration. That possibility has inspired deep underground experiments, placed beneath mountains or inside mines to shield them from ordinary cosmic rays. The detectors wait in extraordinary quiet, watching for the faintest bump from the dark. There is something almost meditative about it. Huge machines built not to create noise but to listen for one nearly silent event. So far, the simplest versions of these candidates have remained undetected. That does not mean the idea is dead, but it has been squeezed. Experiments have become more sensitive, and each non-detection rules out more possibilities. The search continues, but the once wide-open territory has narrowed. Dark matter, if it belongs to this family, may interact even more weakly than expected, have a different mass range, or hide in a more complicated dark sector. A dark sector is a particularly interesting idea. Instead of one lonely dark particle, perhaps there is a whole hidden family of particles and forces, mostly disconnected from ordinary matter. We have the familiar particles that make atoms, light, and chemistry. Maybe dark matter belongs to its own hidden world, with its own interactions, perhaps even dark versions of forces that affect only dark particles. This sounds like science fiction, but it is a serious possibility in theoretical physics. The visible universe may be only one side of a larger particle story. Dark matter may not be just one ingredient, but a whole quiet pantry. Of course, if the dark sector interacts very little with us, it becomes difficult to test. Science needs evidence, not just imaginative architecture. The challenge is to find any connection between the dark sector and the visible one. Perhaps dark particles can occasionally collide with ordinary particles. Perhaps they can annihilate or decay in ways that produce detectable signals. Perhaps they influence the shapes of halos or the behavior of galaxy clusters. Each possibility becomes a thread scientists can pull. Another major candidate is the axion, a hypothetical particle originally proposed for reasons that had nothing to do with dark matter. This is one of the charming habits of physics. A particle invented to solve one problem may wander into another problem wearing a convincing hat. Axions would be extremely light, far lighter than the typical massive particle candidates, and they would interact very weakly with ordinary matter. If produced in the early universe, they could behave as cold, dark matter, gathering under gravity while remaining almost invisible. Axions are strange because their lightness makes them less like tiny marbles and more like a field spread through space. Depending on their properties, they might form wave-like patterns on cosmic scales. They are searched for with experiments that use powerful magnetic fields and delicate instruments, hoping to convert axions into detectable light under the right conditions. Again, the effort is patient and exacting. It is like trying to hear one particular whisper in a thunderstorm, except the thunderstorm is made of ordinary particles, instrument noise, and the general inconvenience of reality. There are also sterile neutrinos, hypothetical cousins of ordinary neutrinos. Ordinary neutrinos interact through the weak nuclear force, though very rarely. Sterile neutrinos would interact even less, perhaps only through gravity and tiny mixing with ordinary neutrinos. If they have the right mass and properties, they could contribute to dark matter. They would not be as fast as ordinary light neutrinos, and they might affect structure formation in distinctive ways. Scientists have searched for possible signals from sterile neutrino decay, especially faint X-ray lines from galaxies and clusters. Some hints have appeared over the years, but nothing has become conclusive enough to settle the matter. Then there are primordial black holes. These are not black holes formed from dying stars. They would have formed in the early universe, possibly from dense regions collapsing under their own gravity. If such black holes were abundant and had suitable masses, they could behave as dark matter. This idea has risen and fallen in popularity more than once. Black holes are certainly dark in the simple sense that they do not emit light from within the horizon, and they have gravity. But they are not particles. They are compact objects. Observations place strong limits on how many primordial black holes can exist in many mass ranges. They might still make up some fraction of dark matter, or perhaps all of it in certain allowed windows. But the idea faces serious constraints. Primordial black holes are appealing because they do not require a new particle. They require unusual conditions in the early universe, but black holes themselves are part of known gravity. Still, making them account for all dark matter without conflicting with observations is difficult. They could affect starlight through lensing, disturb star clusters, influence cosmic backgrounds, or merge and produce gravitational waves. Each of these possibilities gives astronomers ways to test the idea. The mystery remains open, but not freely open. It is fenced in by evidence. Some candidates are even more delicate. Ultralight dark matter, sometimes imagined as extremely light particles spread across enormous distances, could behave like a wave on galactic scales. If dark matter is like this, it might smooth out the centers of small galaxies or create interference patterns in halos. Such models can help address certain small-scale puzzles, though they too must satisfy many constraints. This kind of dark matter asks us to think less in terms of particles flying around like invisible dust, and more in terms of fields filling space. It is not easy to picture, but then again neither is ordinary quantum physics, and that has not stopped it from being correct with almost irritating success. There are also ideas involving self-interacting dark matter. In the simplest, cold dark matter picture, dark matter particles mostly ignore each other except through gravity, but perhaps they bump into each other through a dark force, not strongly enough to make them behave like ordinary gas, but enough to change the shapes and central densities of halos. This could help explain some features of galaxies and clusters, depending on the details. It would mean dark matter is not completely antisocial, just selective about its company. It may ignore us, but interact with itself in the dark. The challenge with all these candidates is that each must pass several different tests at once. It must match the abundance of dark matter. It must form the right cosmic structures. It must avoid detection in ways consistent with experiments. It must not disrupt the early universe in ways that contradict observations. It must behave properly in galaxies, clusters, and the cosmic web. A candidate can sound wonderful in one setting and fail badly in another. The universe is an examiner with many pages of questions. This is why the dark matter problem has lasted so long. It is not that scientists have no ideas. They have many ideas. The difficulty is finding one that nature has actually chosen. The candidates hide in different ways. Some are heavy and rare in their interactions. Some are light and field-like. Some are compact, ancient objects. Some belong to hidden sectors. Some might produce faint signals in detectors. Some might reveal themselves only through their influence on galaxy structure. The search is broad because the mystery is broad. It is worth pausing here to notice how strange the situation really is. We live in a universe where the ordinary matter we know, the matter of stars, planets, air, water, skin, paper, and warm blankets, appears to be only a minority of the matter. The dominant form does not take part in chemistry. It does not make atoms as we know them. It does not form shining surfaces or familiar objects. It mostly passes through itself and through us, gathering only through gravity into halos and filaments. We have named it dark matter, but the name is more like a placeholder than an explanation. It is a label on a locked box. Still, the locked box is not empty. The clues are real. The motions of galaxies are real. The lensing of light is real. The cosmic web is real. The question is whether the key will be found in a mine deep underground, in a radio signal from an Axion experiment, in a gravitational wave pattern, in the detailed mapping of dwarf galaxies, in a particle collider, or in some observation no one has yet imagined. Scientific mysteries often look impossible until the right tool is built. Before radio astronomy, the universe had voices we could not hear. Before X-ray telescopes, hot gas in clusters was mostly hidden. Before gravitational wave detectors, merging black holes were silent to our instruments. Dark matter may require another such leap. There is a gentle humour in the fact that dark matter candidates often sound like characters from a very quiet masquerade. The massive particle in a heavy cloak, the axions slipping through a magnetic doorway, the sterile neutrino refusing nearly all conversation, the primordial black hole sitting compactly in the corner, insisting it has been there since the beginning. The ultralight field spread across the room so thinly that no one can decide whether it is a guest or the wallpaper. Each has a reason to be considered. Each has problems. Each waits under the same dim light of uncertainty. But the search is not random. Scientists are not simply inventing names and hoping one feels cosmic enough. Each candidate comes from attempts to solve real problems in physics or cosmology. Each produces predictions. Each can be tested, narrowed, challenged, or rejected. This is what keeps the field scientific rather than merely speculative. The dark may be large, but the methods are disciplined. The main thing these candidates share is that they ask us to loosen our attachment to the familiar. Matter does not have to shine. It does not have to form atoms. It does not have to sit on a table or reflect in a mirror. The word matter means something broader in physics than everyday experience suggests. It means something with energy and mass, something that can gravitate, something that can influence the structure of the universe. dark matter may be matter without light, mass without chemistry, presence without touch. That can feel unsettling, but it can also feel strangely peaceful. The universe is never promised to be built only from things that are easy for human senses to understand. Our senses evolved for warm ground, daylight, food, weather, voices, and nearby danger. They were not designed for invisible halos around galaxies or particles that rarely interact. Science extends those senses. It gives us instruments, mathematics, and careful inference. It lets us notice the hidden architecture behind the shining view. The strange candidates hiding in the dark are therefore not just possible answers. They're invitations to think more deeply about what the universe can contain. Perhaps dark matter is one new particle. Perhaps it is a family. Perhaps it is an ancient population of black holes. Perhaps it is something we have not yet named properly. Perhaps the right answer will seem obvious after it is found, as many discoveries do in hindsight, and future students will wonder why it took so long. Or perhaps it will remain difficult, subtle, and slightly rude for quite some time. For now, the candidates wait in the dark because the dark is where the evidence points. We know the hidden mass must be there in some form. We know it helped shape galaxies and the cosmic web. We know it cannot be mostly ordinary dim matter. We know ordinary neutrinos are not enough. Beyond that, the possibilities open like a set of quiet doors along a corridor. Some doors lead to heavy particles, some to light fields, some to hidden forces, some to ancient black holes. Some may lead nowhere at all. The next step is to look more closely at the most famous of these possibilities, the ones that have shaped decades of experiments and arguments. They are not merely names on a list. They represent different visions of the dark universe. One imagines dark matter as heavy, rare to interact, and waiting to tap an underground detector. Another imagines it as almost unimaginably light, a faint field that might reveal itself through subtle conversions and waves. Others sit between or beyond those extremes. The search for dark matter is not one hunt, but many hunts at once, all guided by the same gravitational footprints. Somewhere in that hidden territory, if the dark matter picture is right, is the answer to what most matter in the universe really is. It may be passing through us now. It may be spread through the galaxy as an invisible sea. It may be gathered in halos around every bright island of stars. It may have been present before the first star ever shone, helping prepare the places where light would eventually appear. And although it does not speak in photons, does not shine in the telescope, does not warm the hand or cast a shadow on the wall, it has been shaping the universe all along, quietly waiting for us to become clever enough to ask the question in the right way. The list of possible dark matter candidates can feel at first like a cabinet full of keys, each one cut for a lock we have not found yet. Some keys are heavy and old, polished by decades of theoretical work. Some are light and strange, almost too delicate to imagine as the source of so much cosmic gravity. Some belong to ideas that began in particle physics for completely different reasons, then wandered into cosmology and found themselves unexpectedly useful. The names can sound peculiar, sometimes almost playful, but behind them are serious attempts to answer a very plain question. What kind of thing could make up most of the matter in the universe, while remaining almost completely hidden from ordinary sight? Among the most famous candidates are WIMPs. The name is an abbreviation, but said aloud it sounds oddly unimpressive for something that might outweigh all the stars and planets by a large margin. A WIMP is a weakly interacting massive particle. In ordinary language, that means a particle with significant mass that does not interact much with normal matter. It would feel gravity. It might feel one of the nuclear forces very faintly, but it would not interact with light, so it would not glow, reflect, block starlight in any simple way, or gather into ordinary objects. It would be present by its pull, not by its shine. For a long time, WIMPs were the leading dark matter candidate. They had a certain elegance that physicists enjoy, the sort of elegance that makes several separate clues seem to point toward the same place. In the early universe, when space was hot and dense, particles were constantly being created, destroyed, scattered, and transformed. If WIMPs existed then, they would have been part of that restless particle crowd. As the universe expanded and cooled, interactions became less frequent. At some point, the number of WIMPs would have settled into a leftover abundance. Under quite natural assumptions, that leftover amount could be close to the amount of dark matter astronomers infer today. This coincidence made WIMPs attractive. It seemed as though the early universe might have produced the right amount without any delicate adjustment. A particle with the right mass and the right weak interaction strength could naturally remain as a cosmic relic. It would drift through the universe, gather into halos under gravity, and quietly shape galaxies. It would be born from particle physics and confirmed by astronomy. That is the kind of story scientists like, not because it is pretty, although it is, but because it connects different parts of nature. There was another reason WIMPs felt promising. Some theories beyond the known particle physics predicted new particles with just the sort of properties dark matter needed. These theories were not invented only to explain dark matter. They were often developed to solve other problems, such as why certain particle masses have the values they do, or how forces might unify at very high energies. In some versions, the lightest new particle would be stable, electrically neutral, and weakly interacting. That sounds suspiciously like a dark matter candidate arriving at the door already wearing the right coat. So WIMPs became a major focus. Scientists designed experiments to search for them in several ways. One approach is direct detection. If WIMPs fill the halo of the Milky Way, then Earth is moving through a sea of them as the solar system orbits the galaxy. Most would pass through everything without effect, but very rarely perhaps one might strike the nucleus of an atom in a detector. That tiny collision would cause a slight recoil, a faint flash of light, a small amount of heat, or a subtle release of charge depending on the detector. The event would be extremely rare and extremely quiet, so the experiments must be shielded from ordinary radiation that could mimic the signal. This is why many dark matter detectors are placed deep underground. Rock above the laboratory blocks much of the cosmic ray background that constantly rains down on Earth from space. The detectors themselves are built from carefully chosen materials and surrounded by layers of shielding. They are designed to be still, cold, quiet, and patient. In a sense, they are listening for one whisper while the rest of the universe coughs, hums, clicks, and rustles. If a WIMP bumps into an atomic nucleus, the detector should notice. The problem is that ordinary particles can also create tiny signals, and nature is very good at producing misleading little noises. Over the years, these experiments have become astonishingly sensitive. They have looked for WIMPs across a wide range of masses and interaction strengths. Some experiments use liquid xenon. Some use germanium crystals. Some use argon. Some are designed to detect heat. Others light. Others charge. They are different kinds of traps for the same nearly uncatchable visitor. So far, no widely accepted WIMP signal has appeared. This does not mean WIMPs are impossible, but it has ruled out many of the simplest and most hopeful versions. The once broad road has become narrower. If WIMPs exist, they may interact even more weakly than expected, or have properties that make them harder to find than early models suggested. There is also indirect detection. If WIMPs can collide with one another and annihilate, they might produce ordinary particles such as gamma rays, neutrinos, or antimatter particles. Scientists therefore look toward places where dark matter should be dense, such as the centers of galaxies, dwarf galaxies, or galaxy clusters, hoping to spot unusual radiation that cannot be explained by ordinary astrophysical sources, but the universe is not a quiet background. It contains pulsars, black holes, supernova remnants, cosmic rays, and all manner of energetic objects that can produce confusing signals. Separating a possible dark matter glow from ordinary high-energy astrophysics is difficult. A signal must have the right distribution, the right energy pattern, and the right lack of ordinary explanation. Hints have appeared from time to time, but none has settled the case. A third route is production in particle colliders. If WIMPs can be created in high-energy collisions, then machines that smash particles together might produce them. Since WIMPs would escape the detector without interacting, scientists would not see the WIMP itself. They would infer it from missing energy and momentum in the collision debris. The basic idea is that if you know what went in and you measure what came out, an invisible particle may reveal itself by what seems to be missing. This is a clever method, but again the results have not delivered a confirmed WIMP. The search continues, and the absence of discovery has pushed physicists to think more broadly. That broadening is healthy. A good mystery should not become trapped inside one favourite answer. WIMPs may still exist, but dark matter may be something else entirely. One of the strongest alternatives is the axion. If WIMPs are like heavy, quiet particles moving through the galaxy, axions are more like an almost weightless murmur spread across space. They were not originally invented as dark matter. They emerged from a problem in the theory of the strong nuclear force, the force that helps hold atomic nuclei together. The details are technical, but the important point is that the axion was proposed to explain why this force seems to respect a certain symmetry much more perfectly than one might expect. Later, scientists realized that axions produced in the early universe could behave like dark matter. This is a beautiful twist. A particle imagined to solve a puzzle inside atomic nuclei might also explain the hidden mass around galaxies. It is like finding a key under the sofa and discovering that it opens a door in another house. Axions would be extremely light and extraordinarily difficult to detect. Yet there is a possible way to search for them. Under certain conditions, an axion might convert into a photon, a particle of light, in the presence of a strong magnetic field. Experiments designed to find axions use this possibility. Some look for axions that might make up the dark matter halo of our galaxy. Others look for axions that might be produced in the sun. The instruments are delicate, often involving powerful magnets, resonant cavities, ultra-sensitive electronics, and careful tuning. They are not waiting for a heavy particle to hit an atom. They are trying to coax a faint hidden field into producing a tiny detectable signal. The axion search has a different feeling from the WIMP search. WIMP detectors often wait for rare impacts. Axion detectors often tune themselves like radios, scanning possible frequencies where an axion signal might appear. Imagine trying to find a radio station broadcasting from the dark matter halo, but you do not know the station's frequency. The signal is incredibly faint, and the radio must be colder and quieter than almost anything in the room. It is a slow scan through possibility. Axions are appealing because they can be dark, stable, abundant, and cold enough to form cosmic structures. Depending on their mass, they might behave in ways almost indistinguishable from ordinary cold dark matter on large scales, while producing subtle differences on smaller scales. Some versions of axion-like particles could be much lighter or have different couplings than the original axion. This opens a vast landscape of possibilities. That is exciting, but also challenging, because a wide landscape means many places to search. There is another family of ideas that sits somewhere between known particles and unknown dark sectors. Sterile neutrinos are one example. Ordinary neutrinos already exist and already behave in a ghostly way. They pass through matter almost freely, interact only rarely, and have tiny masses. But ordinary neutrinos move too quickly to be the main dark matter. Sterile neutrinos, if they exist, would be even more elusive. They would not participate in the usual weak interactions, except perhaps through tiny mixing with ordinary neutrinos. With the right mass, they could act as a warmer form of dark matter, not as fast as ordinary neutrinos, but not as sluggish as the simplest cold dark matter candidates. Warm dark matter would change the formation of small structures. It could reduce the number of tiny halos compared with cold dark matter. This has made sterile neutrinos interesting in discussions of small galaxy counts and dwarf galaxy structure. They might also decay very slowly, producing faint X-ray signals. Scientists have searched for such signals in galaxies and clusters. Over the years, there have been reports of possible unexplained X-ray features, but the interpretation remains uncertain. Astrophysical backgrounds, instrument effects, and ordinary atomic emission can complicate the picture. The sterile neutrino remains a suspect, not a convicted culprit. Then there are dark photons and other hidden force carriers. The name dark photon can be misleading if it suggests dark light shining in a dark room. A dark photon would be a particle associated with a hidden force, somewhat analogous to how the photon is associated with electromagnetism, but mostly affecting dark sector particles. In some theories, dark matter is not just one particle floating silently through space. It belongs to a hidden sector with its own particles and forces. The dark sector might communicate with ordinary matter through tiny portals, faint connections that could allow rare interactions or decays. This idea is attractive because the visible particle world is already rich. Ordinary matter is not made of only one particle. It includes quarks, electrons, neutrinos, photons, gluons, and more. It has forces, structures, bound states, reactions, and histories. Why should the dark side of matter be limited to one simple particle? Perhaps it is simple, but perhaps it is not. A hidden sector could include multiple dark particles, dark forces, and even dark forms of cooling or structure, though these must be limited by observations. If dark matter interacted too strongly with itself, or radiated too much dark energy, it might form disks, clumps, or other structures not seen. But a moderately complex dark sector remains possible. Self-interacting dark matter is another important possibility. In the standard cold dark matter picture, dark matter particles hardly collide with one another. They pass through each other like quiet strangers in a very large train station. But maybe they interact among themselves through a hidden force. These self-interactions could soften the dense centers of dark matter halos, or change the shapes of halos in ways that might better match some observations. They could also affect collisions between galaxy clusters. Too much self-interaction is ruled out because dark matter in colliding clusters appears to pass through relatively freely. But a small amount might still be allowed and interesting. This is a good example of how dark matter research is not only about detection in a laboratory. The behavior of galaxies and clusters can reveal particle properties. If dark matter particles scatter from each other, even rarely, the structure of halos changes over billions of years. A galaxy becomes a long experiment conducted by nature. A cluster collision becomes a vast particle physics test, with galaxies, gas, and dark matter moving through one another on scales no laboratory could build. Astronomers measure the aftermath and ask what kind of dark matter could behave that way. Another possibility, very different in spirit, is ultralight dark matter. These particles would be so light that their quantum wave nature becomes important on galactic scales. Instead of behaving like individual particles in the usual everyday imagination, they could form wave-like patterns across halos. This might smooth out small-scale structure and produce distinctive effects in dwarf galaxies and in the distribution of matter along cosmic filaments. Such ideas are sometimes called fuzzy dark matter, a name that sounds almost too cozy for a serious theory, but the physics behind it is real. The fuzziness refers not to softness in a blanket sense, but to the fact that the particle's wave nature prevents it from clumping below certain scales. Ultralight dark matter is fascinating because it changes the picture of what a halo is. A dark matter halo would not simply be a swarm of heavy invisible particles orbiting in random directions. It might have a coherent wave structure, with interference and pressure like effects arising from quantum mechanics. This could alter the centers of galaxies and the abundance of very small halos. But as with every candidate, it must satisfy many constraints. It must form the cosmic web correctly. It must match observations of distant gas clouds, galaxy formation, and gravitational lensing. Some versions are strongly constrained, others remain possible. There are also asymmetric dark matter models. These take inspiration from a known feature of ordinary matter. The universe contains much more matter than antimatter, at least in the regions we observe. Why this imbalance exists is a major question. Some theories suggest dark matter may have its own matter-antimatter imbalance, and that the amount of dark matter might be linked to the amount of ordinary matter through processes in the early universe. In such models, dark matter is not just a leftover from particles freezing out of equilibrium. It is connected to the same cosmic history that allowed ordinary matter to survive. This can explain why the amounts of ordinary matter and dark matter are different, but not wildly unrelated. It is an elegant thought, though still speculative. There are candidates called primordial black holes, although they are not ghostly particles in the same sense. If black holes formed in the early universe from dense regions collapsing, they could contribute to dark matter. They would be dark, massive, and long-lived if large enough. But they would be compact objects, not diffuse particles. Observations constrain them strongly in many mass ranges. If they were too common, they would produce lensing events, disrupt stellar systems, affect cosmic backgrounds, or show up through gravitational wave mergers in ways we could notice. Still, there remain debated windows where primordial black holes might contribute some or all of dark matter. They're a reminder that dark matter candidates are not limited to new particles, though most evidence points away from ordinary compact objects as the full answer. A different kind of possibility is that dark matter may be made of particles that are extremely difficult to produce or detect, because they are connected only through gravity. Such particles would be almost completely hidden from laboratory experiments, except through their cosmic effects. This is scientifically frustrating, because a candidate that only interacts gravitationally is hard to test directly. But it is not impossible to study indirectly. Its abundance, distribution, and influence on structure still matter. The sky becomes the detector. The phrase ghostly possibilities is useful, but it should be understood carefully. These candidates are not ghosts in a supernatural sense. They are ghostly because they pass through the ordinary world with little disturbance. They do not fit the matter we know from daily life. They may be present in every room, and yet leave no mark on the furniture. They may flow through Earth by the billions or trillions without touching an atom in a meaningful way. This is strange, but not magic. It is what happens when particles lack the interactions that make ordinary matter feel solid, visible, and warm. Solidity itself is not as simple as it feels. When your hand rests on a table, the sensation of firmness comes from electromagnetic forces between atoms. The atoms in your hand and the atoms in the table do not pass through each other, because their electron clouds resist overlap. Light reflects from the table, because electrons interact with photons. Heat moves through the table because atoms and electrons exchange energy. Dark matter seems not to participate in those electromagnetic conversations. Without that, it cannot make a table, cannot reflect light, cannot feel solid to your hand. It can share space with ordinary matter almost unnoticed. This also explains why dark matter does not form dark stars and dark planets in the familiar sense. Ordinary gas clouds can cool by radiating light. As they lose energy, gravity pulls them tighter, and eventually stars can form. Dark matter does not seem to radiate energy efficiently. It can gather gravitationally, but it cannot easily shed the motion that keeps it spread out, so it forms broad halos rather than compact shining objects. If there are dark forces that allow some cooling in a hidden sector, the picture could become more complicated, but observations limit how much of that can happen. The main dark matter component appears to remain diffuse. Every candidate must respect this behaviour. A good dark matter particle cannot interact too strongly with light, ordinary matter or itself, unless the interactions are arranged carefully enough not to spoil galaxies and clusters. It must be invisible, but not irrelevant. It must be quiet, but gravitationally powerful. It must be stable, but not frozen out of cosmic history entirely. These requirements make the search narrow in some ways and vast in others. The most difficult part is that dark matter has not yet given a non-gravitational signal that everyone agrees on. There have been hints over the years. Some experiments have reported signals that might have been dark matter, only for other experiments to fail to confirm them. Some astronomical observations have shown excess radiation that might come from dark matter, but might also come from ordinary astrophysical sources. This is normal in frontier science. The edge of knowledge is messy, instruments improve, backgrounds are better understood, claims rise, sharpen, fade, or sometimes survive. A confirmed discovery requires not only a signal, but a signal that can withstand every reasonable attempt to explain it away. WIMPs remain important partly because the search for them has driven enormous experimental progress. Even non-detections teach us something. They rule out possible masses and interaction strengths. They force models to become more precise. They encourage new detector technologies. The same is true for axions. The search has expanded into new mass ranges, new methods, and increasingly sensitive instruments. Sterile neutrinos, dark photons, self-interacting models, and ultralight fields all motivate different tests. The failure to find one candidate does not empty the mystery. It rearranges the map. One of the most interesting possibilities is that dark matter may not be one thing. Ordinary matter is not one thing, so perhaps dark matter is mixed too. There could be a dominant component and smaller subcomponents. Perhaps most dark matter is one kind of particle, with a fraction in another form. Perhaps primordial black holes contribute a little. Perhaps sterile neutrinos or axion-like particles contribute some portion. This would make the story more complicated, but the universe has never shown a strong commitment to keeping things simple for our benefit. A mixed dark matter universe would be harder to decode, but not impossible. At the same time, simplicity remains valuable. The simplest cold dark matter model, with a stable non-luminous particle interacting mainly through gravity, explains a remarkable amount about the large-scale universe. That success cannot be ignored. Any more elaborate candidate must preserve what works while improving what does not. Scientists are not looking for strangeness for its own sake. They are looking for the simplest and most testable explanation that matches all the evidence. The names can sometimes hide the larger meaning. WIMPs, axions, sterile neutrinos, dark photons, fuzzy particles, primordial black holes. It can sound like a roll call in a very unusual classroom, but each name represents a different answer to the question of how the universe can contain matter that does not shine. Each answer changes the story of the early universe. Each affects how galaxies formed. Each suggests different experiments and observations. Each gives dark matter a different personality. If WIMPs are right, then dark matter may be a heavy relic from the hot early universe, still passing through us in a faint cosmic wind, occasionally close enough to touch a nucleus but almost always slipping by. If axions are right, dark matter may be an incredibly light field filling space, waiting to reveal itself through subtle electromagnetic conversions. If sterile neutrinos are right, dark matter may be related to the ghostliest particles we already know, but hidden one step further. If self-interacting dark matter is right, the dark sector may have its own quiet social life, influencing halo shapes over time. If ultralight dark matter is right, galaxies may be shaped by waves of an almost unimaginable scale. If primordial black holes are right, at least some dark matter may be made of ancient gravitational fossils from the universe's first moments. Each possibility is strange, but the fact that dark matter exists at all, if the evidence is interpreted correctly, is already strange. We should not expect the answer to feel ordinary. There is a calming way to think about this. The universe is not refusing to explain itself. It is giving explanations in languages we are still learning. Galaxy rotation is one language, the cosmic web is another, particle experiments are another, X-ray searches, gravitational lensing, dwarf galaxy counts, underground detectors, magnetic cavities, collider events, and cluster collisions are all different attempts to translate the same hidden sentence. Somewhere among them may be the phrase that tells us what dark matter is. Until then, the candidates remain ghostly because our contact with them is incomplete. We know the outline of the absence, we know the weight of the invisible, we know the effect without the identity. But this is not ignorance in the empty sense. It is informed ignorance, which is one of the most productive states in science. It means the question has shape. It means wrong answers can be ruled out. It means the darkness is not featureless. It has boundaries, clues, and pressure points. As the search continues, experiments become quieter, telescopes more precise, simulations more detailed, and theories more constrained. A future discovery might arrive as a tiny flash in an underground detector, a narrow line in a cosmic spectrum, an unexpected behaviour in a dwarf galaxy, a pattern in gravitational lensing, or a particle produced in a collider and recognised by what it carries away unseen. It might come from a place already being watched, or from a method not yet invented. That uncertainty is part of the appeal. For now, dark matter remains a hidden majority with many possible faces. WIMPs gave scientists a powerful and testable dream. Axions offer a lighter and subtler path. Sterile neutrinos, dark sectors, self-interactions, ultralight fields, and primordial black holes keep the field open and restless. The universe has not yet told us which of these, if any, is correct. But it has told us that the answer matters. The identity of dark matter is not a small detail tucked into the margins of physics. It is part of the origin story of galaxies, clusters, and the cosmic web. It is part of why the universe has the shape it does. And so the ghostly possibilities remain with us, not as fantasies, but as disciplined guesses standing in the long shadow of evidence. They drift through theories, detectors, and sky maps, each one trying to match the gravitational footprints left across space. The next question is how scientists attempt to catch something that barely touches anything at all, how they build instruments for the nearly invisible, and how a universe full of silence might still be persuaded to give one small, decisive answer. Trying to find dark matter is a little like trying to catch a shadow that has weight. You know it is there because the floorboards bend, the furniture shifts, and the whole house behaves as though something heavy is standing nearby. But when you turn on the lamp, nothing appears. You try a brighter lamp, then a different lamp, then a lamp so sensitive it can notice a single wandering particle, and still the thing refuses to show itself directly. This is the problem scientists face. Dark matter has gravity, and gravity has told us a long, consistent story. Yet gravity is also the weakest of nature's familiar influences, and if dark matter speaks only through gravity, then catching it in a laboratory becomes almost absurdly difficult. Still, scientists are not easily discouraged by absurdly difficult things. Much of physics has been built by asking nature questions so carefully that even the quietest answers can be heard. The search for dark matter is one of the most patient questions ever asked. It happens deep underground, high in orbit, inside particle colliders, through radio dishes, across maps of galaxies, and in the subtle bending of light that has travelled for billions of years. There is no single dark matter experiment. There is a whole landscape of attempts, each designed around a different possibility for what dark matter might be. The first kind of search is often called direct detection. The name sounds straightforward, almost too straightforward, because the actual method is anything but simple. The basic idea is this: if dark matter fills the halo of the Milky Way, then the Earth is moving through that halo as the Sun orbits the galaxy. In that case, dark matter particles should be passing through Earth all the time. Most would pass straight through the planet without noticing it, just as they pass through stars, dust, and human bodies, with almost no interaction. But if dark matter particles have even the tiniest ability to bump into ordinary matter, then once in a great while, one might strike an atomic nucleus inside a detector. That tiny strike would be the signal, not a bright flash like lightning, not a crack in the floor. More like a single tap on a door in a mansion during a storm. The detector has to notice that tap, identify it, and prove it was not caused by any of the countless ordinary particles that are also passing through the world. Cosmic rays from space, radioactive traces in the materials, particles from the surrounding rock, even tiny amounts of contamination can create signals that imitate what dark matter might do. So, direct detection experiments are built like temples of quiet. Many of them are placed deep underground, beneath mountains or in old mines. The rock above them acts as a shield, blocking much of the shower of high-energy particles that constantly rains down from space. Even deep underground, the detectors must be surrounded by layers of shielding. The materials used to build them are chosen for extraordinary purity, because even a small amount of natural radioactivity can make too much noise. The instruments are kept cold, stable, and isolated. Scientists spend years learning every background signal, every unwanted vibration, every faint source of interference. They are not merely building a machine, they are building an environment where a nearly impossible event might be recognized. Some of the most sensitive detectors use liquid xenon. Xenon is a heavy noble gas, which means it does not readily react chemically with other substances. When cooled into liquid form and placed in a carefully designed detector, it can respond to a particle interaction with tiny flashes of light and released electrons. If a dark matter particle struck a xenon nucleus, the collision would produce a small recoil. The detector would measure the light and charge from that recoil, using the pattern to distinguish possible dark matter events from background radiation. Xenon is useful because its nuclei are heavy, which can make them good targets for certain dark matter candidates, and because it can be purified very well. Other experiments use liquid argon, germanium crystals, silicon, sodium iodide, or other materials. Each target has advantages. Some are better for heavier dark matter particles, some can search for lighter candidates, some measure heat, some measure light, some measure electric charge, and some measure more than one signal at once. This variety is important because no one knows what dark matter is. If you're fishing in a dark ocean for an unknown creature, it is wise not to bring only one kind of net. The challenge is that a true dark matter signal must be rare, repeatable, and consistent with expectations. One event is not enough. A few events are not enough if they can be explained by background noise. Scientists need a pattern that survives scrutiny. They need to know where the signal appears in the detector, how energetic it is, whether it changes over time, and whether other experiments can confirm it. Dark matter detection is not about seeing something odd and declaring victory. It is about ruling out the ordinary with almost unreasonable care. There is an interesting expected feature in some direct detection searches. Because Earth orbits the Sun while the Sun moves through the galaxy, our speed through the dark matter halo should change slightly during the year. At some times, Earth's orbital motion adds a little to the Sun's motion through the halo. At other times, it subtracts a little. This could produce a yearly variation in the rate of dark matter interactions. Some experiments have looked for such a seasonal pattern. There have been claims of annual modulation signals, but other experiments using different materials and methods have not confirmed them in a way that satisfies the broader community. The result is one of those long-running scientific tensions that refuses to become either a clean discovery or a simple dismissal. Direct detection is the most literal way to catch dark matter, but it is not the only way. Another approach is indirect detection. Instead of waiting for dark matter to hit a detector on Earth, scientists look into space for products of dark matter interactions. If certain dark matter particles can collide with each other and annihilate or decay very slowly, they might produce ordinary particles such as gamma rays, neutrinos, electrons, positrons, or antiprotons. These products could travel through space and be detected by telescopes or particle observatories. The best places to look are regions where dark matter should be dense. The centre of the Milky Way is one candidate, because dark matter is expected to be more concentrated there. Dwarf galaxies are another, and in some ways cleaner. Dwarf galaxies can contain a lot of dark matter relative to their visible stars, but they have fewer ordinary astrophysical sources that produce confusing high-energy radiation. Galaxy clusters are also targets, as are regions of the sky where dark matter annihilation might create a faint diffuse glow. Gamma-ray telescopes search for high-energy light that could come from dark matter annihilation. Neutrino observatories look for elusive particles that might be produced if dark matter gathers in the Sun or Earth and annihilates there. Cosmic ray detectors measure antimatter particles that might be produced by dark matter processes. Each method faces the same basic difficulty. The universe is full of ordinary things that can produce energetic particles. Pulsars, supernova remnants, black holes, cosmic ray collisions and hot gas can all create signals that may resemble dark matter. A possible excess is not automatically a discovery. It must have the right energy, direction, distribution, and consistency with other observations. This makes indirect detection a delicate form of astronomy. Scientists are looking not only for a signal, but for a signal that ordinary astrophysics cannot easily explain. Sometimes there are tantalizing hints. A gamma-ray excess near the center of the Milky Way, for example, has generated much discussion. Could it be dark matter? Could it be a population of unresolved pulsars? Could it be some more complex behavior of cosmic rays? The debate shows how difficult the search is. Dark matter may be quiet, but the galaxy is not. The center of the Milky Way is crowded, energetic, dusty, magnetized, and full of sources that are hard to model. It is not exactly the place one chooses for a peaceful afternoon of clean data. Dwarf galaxies are quieter, which is why they are so valuable. They are small galaxies with relatively few stars, often orbiting larger galaxies like the Milky Way. Many appear to be dominated by dark matter. If dark matter annihilation happens, dwarf galaxies could produce detectable gamma rays without too much interference from ordinary sources. So far, searchers have placed strong limits on many dark matter models, but have not produced a confirmed signal. Again, absence matters. Non-detections narrow the possibilities. They tell us which kinds of dark matter cannot be common, or cannot interact in certain ways. Then there is the collider approach. If dark matter is a particle, perhaps it can be produced in high-energy collisions. Particle colliders accelerate ordinary particles to enormous speeds and smash them together, creating conditions that briefly resemble the hot early universe. If the collision energy is high enough, new particles can appear. If dark matter particles are produced, they would likely escape the detector without interacting, leaving no direct track. Scientists would infer their presence from missing energy and missing momentum. Something invisible would have carried away part of the collision's balance. This is a clever method, but it has limits. Colliders can produce particles only if they are light enough and connected strongly enough to ordinary particles to be created at measurable rates. If dark matter is too heavy, too weakly connected, or produced in ways outside the collider's reach, it will not appear. Also, missing energy can have other causes, including known particles such as neutrinos, so collider searchers must look for distinctive patterns, often involving visible particles recoiling against invisible ones. These searchers have not found dark matter yet, but they have ruled out many models and continue to test the connections between dark matter and known particles. The three main strategies for particle dark matter, direct detection, indirect detection, and collider production, form a kind of triangle. Direct detection asks whether dark matter in the galaxy can strike ordinary matter on Earth. Indirect detection asks whether dark matter in space can produce visible particles. Collider searches ask whether ordinary particles can produce dark matter. If the same particle is responsible, these methods may eventually meet. A signal in one could guide the others. If a detector underground sees a possible dark matter particle, colliders might search for related interactions. If telescopes see an annihilation signal, direct detection experiments might test compatible models. The dream is not just discovery but cross-confirmation. Yet dark matter may not be a WIMP-style particle, and so scientists have built other kinds of searches. Axion experiments are among the most elegant. If axions make up dark matter, they may be present as a field throughout the galaxy. Under the right conditions, in the presence of a strong magnetic field, axions could convert into photons. An axion detector is therefore not waiting for a particle to smack into a nucleus. It is trying to convert an invisible dark matter field into a detectable electromagnetic signal. Some axion searches use resonant cavities, devices that can amplify signals at particular frequencies. The experiment is tuned slowly through possible frequencies, like turning the dial on an old radio, except the station being searched for may be broadcasting from the dark matter halo, and the signal is unimaginably faint. The cavity must be cold and quiet. The electronics must be exquisitely sensitive. The magnetic field must be strong. The scanning is slow because each possible axion mass corresponds to a different signal frequency. If the axion exists in the range being searched, the detector might hear a tiny excess of power at just the right frequency. Other axion experiments look for particles produced by the sun. If axions are created in the solar interior, they could stream outward and reach Earth. A strong laboratory magnet might convert them into X-rays. This kind of experiment aims at axions or axion-like particles that interact with light more strongly than some dark matter versions. Still other experiments use carefully designed materials, quantum sensors, atomic clocks, superconducting circuits, or nuclear magnetic techniques to search for different axion couplings. The axion field has inspired a remarkable variety of instruments because the possible mass range is wide and the signals can be subtle. The newer generation of dark matter searches often relies on quantum sensing. This phrase can sound fashionable, but it reflects a real shift. If dark matter is lighter than traditional WIMP candidates, it may not deposit enough energy to produce the usual nuclear recoil signals. Scientists need detectors sensitive to much smaller disturbances, perhaps tiny vibrations in crystals, changes in superconductors, excitations in materials, or shifts in atomic energy levels. The search moves from large rare impacts to delicate continuous whispers. Technology developed for quantum information, precision measurement, and condensed matter physics becomes useful for cosmology. The dark matter problem pulls many fields into the same room. There are also searches for dark photons and hidden sector particles. These might mix faintly with ordinary photons or produce tiny electromagnetic effects. Experiments may use resonant devices, beam dumps, fixed target setups, or precision measurements to look for signs of such particles. The details depend on the model, but the spirit is the same. If there is a hidden sector, perhaps there is a small portal connecting it to ours. Scientists try to build instruments near that portal and wait. Another way to catch dark matter is not by detecting particles at all, but by mapping its gravitational influence with increasing precision. Since gravity is the one interaction we know dark matter has, astrophysical observations remain essential. Gravitational lensing can map dark matter in galaxies, clusters, and along the cosmic web. Strong lensing, where massive objects create arcs or multiple images, can reveal clumps of dark matter. Weak lensing, where many galaxies are slightly distorted statistically, can map large-scale mass distribution. If dark matter has small-scale structure, lensing may detect its fingerprints. For example, if many small dark matter clumps exist without stars, they can perturb the images of lensed quasars or galaxies. These perturbations might reveal invisible subhalos, testing predictions of cold dark matter. Stellar streams provide another method. Around the Milky Way, some streams of stars are remnants of disrupted star clusters or dwarf galaxies, stretched out by gravity into long trails. If a dark matter clump passes through such a stream, it can create gaps or disturbances. By studying those streams, astronomers may infer the presence of invisible structures in the galactic halo. Dwarf galaxies themselves are important detectors. Their internal motions reveal how dark matter is distributed within them. If dark matter is cold and collisionless, it may produce certain central density patterns. If it self-interacts as warm or as ultralight, the patterns may differ. But dwarf galaxies are complicated by ordinary processes such as star formation and supernova feedback. A small galaxy can have its gas pushed around by bursts of star formation, altering the gravitational potential and changing the distribution of stars and dark matter. So scientists compare many systems, use simulations, and try to separate dark matter physics from ordinary astrophysical effects. Galaxy clusters serve as even larger laboratories. In cluster collisions, ordinary gas can be slowed by pressure and shocks, while galaxies and dark matter pass through more freely. By comparing X-ray maps of hot gas with gravitational lensing maps of total mass, scientists can test whether dark matter behaves like collisionless matter or whether it self-interacts significantly. The famous examples of colliding clusters have strongly supported the view that most dark matter does not behave like ordinary gas. It passes through with little resistance. But more subtle studies may reveal whether it has small self-interactions. The early universe also remains a detector of sorts. The ancient microwave background, the afterglow from when the universe became transparent, contains patterns that depend on the amounts and behaviour of ordinary matter, dark matter, radiation, and other components. If dark matter decayed, interacted with ordinary matter, was too warm, or had unusual properties, it could leave traces in this background or in the later distribution of galaxies. Large surveys of galaxies, measurements of distant gas clouds, and maps of the growth of structure all test dark matter models. The universe has been running the experiment for billions of years. We are latecomers reading the output. There is also the possibility of detecting dark matter through gravitational waves, though this is more indirect and model dependent. If primordial black holes make up some or all of dark matter, their mergers could produce gravitational waves. The masses, rates, and distribution of such mergers might reveal whether they are ordinary astrophysical black holes or an ancient population from the early universe. Gravitational waves could also, in more speculative scenarios, probe phase transitions or exotic compact objects related to dark sectors. This field is young, but it shows how every new way of observing the universe becomes another possible window onto dark matter. The practical difficulty in all these searches is not only sensitivity, it is interpretation. A detector may see a small excess, a telescope may find an unexpected glow, a lensing system may show a strange distortion. But nature offers many ordinary explanations before it yields extraordinary ones. Scientists must ask whether the instrument is behaving correctly, whether the background is understood, whether known astrophysics can account for the signal, whether another experiment sees the same thing, and whether the proposed dark matter explanation fits all other constraints. Discovery is not a single shout. It is a careful conversation that gradually leaves no better alternative. This can make the search feel slow, but slow is not the same as stagnant. Every year, the net tightens. Direct detection experiments push interaction limits lower. Axion experiments scan new mass ranges. Telescopes find more dwarf galaxies and map lensing with greater precision. Simulations include more realistic ordinary matter physics. Collider searches test new models. Quantum sensors open territory that older detectors could not reach. Even when no dark matter particle is found, the shape of the unknown changes. The dark room becomes mapped by the walls we keep bumping into. There is something admirable about building an experiment that may spend years waiting for a signal that might not exist in its chosen range. It requires a special kind of scientific patience. These instruments are often huge, expensive, and delicate. Teams of people monitor them, calibrate them, clean them, shield them, and analyse their data with intense care. Much of the work is not glamorous. It involves understanding backgrounds, rejecting false signals and improving sensitivity by small increments. Yet the goal is enormous. A confirmed detection would identify the matter that helped build galaxies. It would connect particle physics with the structure of the cosmos. It would turn dark matter from gravitational evidence into a substance with measured properties. Imagine the moment, if it comes, when several lines of evidence converge. An underground detector observes a repeated signal consistent with a particle of a certain mass. A telescope sees radiation from dwarf galaxies matching the same particle's expected behaviour. A collider finds missing energy events pointing to a related interaction. Or an axion detector finds a narrow signal that repeats, tracks the expected galactic motion, and is confirmed by another experiment using a different method. Such a discovery would not simply answer one question. It would open a new field. Scientists would then ask how dark matter was produced, whether it has partners, whether it interacts with itself, how it shaped the first galaxies, and what else it reveals about the early universe. Of course, the answer may arrive in a less tidy way. It may begin as an oddity in galaxy structure, a pattern in lensing that rules out some candidates and favours others. It may come from the absence of signals in traditional experiments combined with a subtle cosmological clue. It may show that dark matter is not one particle, but a mixture. It may reveal that our assumptions about the halo near Earth were incomplete. Science often finds nature standing not where the spotlight was aimed, but just outside it, looking mildly amused. The search also teaches humility. Dark matter is abundant yet hidden. It shapes galaxies, yet may barely touch a detector. It is everywhere around us if the standard picture is correct, but its presence is not part of everyday sensation. This reminds us that human experience is a very narrow slice of reality. We notice light because our eyes evolved to use it. We notice solidity because atoms interact electromagnetically. We notice heat, sound, and pressure because they matter for survival. Dark matter does not care about these channels. It belongs to a part of reality that life did not need to sense directly. Only by building instruments and following gravity did we learn to suspect it. That suspicion has now become one of the central scientific quests of our time. Not because dark matter is fashionable, but because the evidence is too broad to ignore. The outer parts of galaxies, the motions of clusters, the bending of light, the cosmic web, the ancient microwave background, and the formation of structure all point toward an unseen component. Catching it would mean understanding the invisible foundation beneath the visible universe. So scientists keep trying. They lower detectors deep into Earth. They cool instruments close to absolute stillness. They polish mirrors and tune cavities. They launch telescopes above the atmosphere. They count dwarf galaxies. They map weak distortions in distant starlight. They smash particles together and look for what escapes. They measure the cosmic background and compare it to simulations. They listen in many languages because dark matter has not told us which language it will use. And perhaps that is the right way to hunt the uncatchable. Not with one trap, but with a patient network of questions. If dark matter will not shine, ask how it bends light. If it will not touch often, build a detector quiet enough for the rarest touch. If it will not appear in one mass range, search another. If it hides from laboratories, let galaxies become laboratories. If it refuses to speak loudly, learn to hear the shape of its silence. The invisible skeleton of the cosmos is not beyond inquiry. It is difficult, but difficulty is not a wall. It is more like a long corridor with many locked doors, and science has a habit of trying every handle, then inventing new handles when the old ones fail. The search for dark matter has already changed technology, astronomy, and particle physics. It has taught us how to measure faint signals with extraordinary precision. It has forced theories to become sharper. It has turned galaxies, clusters, and the early universe into tools for understanding the hidden. The next question waiting in the corridor is a challenging one. What if the missing mass is not missing matter at all? What if galaxies are not revealing a hidden substance, but instead showing us that gravity behaves differently than we think on enormous scales? It is not the most widely accepted answer, but it is too important to ignore. After all, gravity has surprised us before. Newton's gravity gave way to Einstein's deeper picture when observations demanded it. Perhaps the dark matter mystery is asking for another change, or perhaps modified gravity is an elegant detour that cannot match the full evidence. Either way, the possibility must be considered carefully, because a good mystery deserves every serious suspect before the final one is named. There is a certain boldness in blaming an invisible substance for the behaviour of galaxies. It is a reasonable boldness supported by many observations, but boldness all the same. When stars move too quickly at the edges of galaxies, when clusters hold together more strongly than their visible matter allows, when light bends as though extra mass is present, the most common explanation is that there really is extra mass. Dark matter is there, unseen but gravitationally active. That answer has worked remarkably well across many scales. It has become the standard picture because it connects galaxy motion, cluster behaviour, lensing, the cosmic web and the early universe into one coherent story. But science is at its healthiest when it allows a quiet second voice to ask, what if the assumption is wrong? What if the missing matter is not matter? What if the problem is not that galaxies contain an invisible substance, but that our theory of gravity is incomplete on very large scales? What if gravity, the old familiar force that keeps our feet on the ground, guides the moon and gathers galaxies, behaves a little differently when accelerations are extremely small or distances are unimaginably vast? Could gravity itself be fooling us? This is not a silly question. It may sound like a desperate escape route at first, as if astronomers misplaced most of the universe and then decided to accuse gravity of hiding it behind the sofa. But history gives the question some dignity. Gravity has fooled us before. For centuries, Newton's description of gravity worked beautifully. It explained falling apples, orbiting planets, tides, cannonballs, and much of the mechanical universe with extraordinary success. It was so successful that it felt final. Then small cracks appeared. The orbit of Mercury did not behave exactly as Newton's theory predicted. Light, according to deeper observations, was affected by gravity in a way that required a new understanding. Einstein's general relativity did not throw Newton away. It revealed Newton's theory as an excellent approximation in ordinary conditions, while showing that gravity was really connected to the curvature of space and time. So when galaxies behave strangely, it is fair to ask whether another deepening of gravity is needed. Perhaps dark matter is like the old idea of an unseen planet invented to explain a strange orbit, and perhaps the real answer is a revised law. Or perhaps dark matter is real, and modified gravity is the tempting wrong turn. The only way to know is to follow the evidence carefully. The most famous attempt to change gravity in response to galaxy rotation is called modified Newtonian dynamics. It is often shortened to MOND, but the name matters less than the basic idea. In ordinary Newtonian gravity, the pull between masses behaves in a familiar way, and the acceleration of an orbiting object depends on the mass pulling it and the distance involved. This works extremely well in the solar system, in laboratories, and in many everyday situations, but galaxies involve extremely tiny accelerations, far smaller than what we normally experience. Modified Newtonian dynamics proposes that at these very low accelerations the usual relationship changes. Gravity, or the response to gravity, behaves differently. With that change, the flat rotation curves of spiral galaxies can be explained without adding large halos of dark matter. This is a striking achievement. It is one reason modified gravity ideas have persisted. Many spiral galaxies follow patterns that Mond describes surprisingly well. In fact, the connection between visible matter and rotation speed in galaxies is very tight. The amount of ordinary matter in a galaxy, its stars and gas, is closely related to how fast the outer parts rotate, Dark matter models can explain this connection, especially with the help of galaxy formation physics, but MOND was designed in a way that naturally captures it. To some scientists, that is a clue that the galaxy data may be trying to tell us something about gravity itself. There is something elegant about that. Instead of saying every galaxy is embedded in an unseen halo arranged just so, modified gravity says the visible matter may be enough if the laws of motion change in the right regime. The stars move as they do because gravity is not quite what we thought at low accelerations. No invisible halo required, at least for the basic rotation curves of many galaxies. If the only evidence for dark matter came from spiral galaxy rotation, modified gravity would be a very strong competitor. It might even feel simpler. After all, adding a vast invisible substance is a large step. Changing a law is also a large step, but if the change explains the data with fewer hidden components, it deserves attention. The problem is that galaxy rotation is not the only evidence. The universe has many witnesses, and they do not all tell the same story in a way that modified gravity handles easily. Galaxy clusters were among the first places where missing mass appeared, and they remain difficult for many modified gravity theories. Even with modified dynamics, clusters often still seem to need extra, unseen mass. Not as much as in the standard dark matter interpretation perhaps, but still some. This is awkward. If the goal is to remove dark matter entirely, galaxy clusters do not cooperate. Some modified gravity supporters have suggested that unseen ordinary matter or neutrino-like particles might supply the remaining mass, but then the clean alternative becomes less clean. It starts to reintroduce invisible matter, though perhaps of a different kind. An even more important challenge comes from gravitational lensing. Any successful theory must explain not only how stars and galaxies move, but how light bends around massive systems. General relativity connects gravity to the paths of light, and observations of lensing are now very precise. Early versions of modified Newtonian dynamics were not complete relativistic theories, meaning they did not fully describe how space, time, and light should behave. Later theories were developed to address this, attempting to reproduce lensing effects without dark matter. Some can do part of the job, but the full range of lensing observations remains challenging. One of the most famous pieces of evidence is a colliding system often called the bullet cluster. It is actually a collision between galaxy clusters. In such a collision, the galaxies mostly pass through one another because the distances between stars are enormous. Dark matter, if it interacts only weakly, should also pass through fairly freely. Hot gas, however, behaves differently. Gas clouds collide, slow down, heat up, and emit X-rays. When astronomers map the hot gas and compare it to the total mass inferred from gravitational lensing, they find that much of the gravitational mass is separated from the ordinary gas. The lensing mass lines up more with the galaxies than with the gas. This is difficult for simple modified gravity explanations because most of the ordinary matter in such clusters is in the hot gas, not in the galaxies. If gravity is being modified based only on visible matter, the strongest gravitational lensing should be tied closely to where most ordinary matter is. But the lensing peaks appear displaced from the gas. This looks very much like a collisionless dark matter component passing through, while the gas is left behind. It is not the only observation of this kind, but it is one of the clearest. For many scientists, systems like this strongly favour dark matter as a real substance, rather than only a change in gravity. The cosmic microwave background also presents a major challenge. This ancient light carries a detailed pattern from the early universe. The relative heights and positions of its temperature variations reveal the contents of the universe with remarkable precision. A universe with ordinary matter, dark matter, and dark energy fits these patterns very well. Dark matter plays a specific role in how early density waves evolved before the first atoms formed. Without a dark matter component, reproducing the observed microwave background becomes extremely difficult. Modified gravity theories can try to adjust the rules, but they must match not only galaxies today, but the early universe as well. That is a much harder task. Large-scale structure adds another test. The cosmic web formed from tiny early density variations growing under gravity. Dark matter helps this growth begin early and proceed efficiently. Ordinary matter was coupled to radiation in the young universe and could not clump freely at first. If there is no dark matter, the formation of galaxies and clusters by the present day becomes harder to explain. Modified gravity might speed up growth later, but it must do so in a way that matches the observed distribution of galaxies, lensing maps, cluster abundances, and the microwave background. Again, the standard dark matter picture has a broad success here that is not easy to replace. This is the central difficulty for modified gravity. It often shines in one area, especially the detailed behavior of galaxy rotation, but struggles to explain the full set of cosmological evidence as cleanly as dark matter does. Dark matter, in contrast, explains many different observations with one main ingredient, though it still has the embarrassing problem that the ingredient has not been directly identified. It is like having a recipe that bakes the cake perfectly, but refuses to reveal what one of the main ingredients is. Modified gravity offers an alternative recipe that works beautifully for one layer, but has trouble with the whole cake unless more ingredients are added. That does not mean modified gravity should be dismissed. It may still be pointing towards something important. Sometimes an idea can be wrong as a complete theory, but right as a clue. The tight relationship between visible matter and galaxy rotation is real. Even within dark matter models, scientists must explain why ordinary matter and dark matter arrange themselves in galaxies in such correlated ways. Galaxy formation is complex, involving gas cooling, star formation, stellar feedback, black holes, mergers, and environmental effects. Perhaps those processes naturally produce the observed patterns. Many simulations are making progress. But the patterns remain important, and modified gravity has helped keep attention on them. There is also the possibility that the final answer involves both dark matter and a deeper understanding of gravity. This is less often discussed in simple presentations because people like clean alternatives. Either dark matter exists or gravity is modified, but nature is not required to honour our preference for tidy debates. Dark matter could be real, and gravity could still have subtle modifications in regimes we have not fully tested. Or a theory that looks like modified gravity on galactic scales might emerge from interactions between ordinary matter and a dark sector. Some researchers explore ideas where the behaviour associated with Moon arises from dark matter with unusual properties, or from new fields that affect gravity and matter in limited ways. Such hybrid ideas are difficult, but they show how the debate can be more creative than a simple contest. The goal is not to defend a team. The goal is to understand why the universe behaves as it does. If dark matter particles are discovered tomorrow in a detector, modified gravity as a full replacement would lose much of its appeal, but the galaxy scale patterns would still require explanation. If a new law of gravity were confirmed in some way, particle dark matter models would have to adapt. Science moves by evidence, not by loyalty. It is useful to ask what kind of observation would clearly favour modified gravity. One possibility would be a repeated precise failure of dark matter models in systems where ordinary matter alone predicts the motion under a modified law. Another would be a laboratory or solar system test showing a deviation from known gravity in the relevant regime, although the accelerations and environments involved are hard to reproduce. A complete relativistic modified gravity theory would also need to match the microwave background, lensing, cluster collisions, and structure formation, without adding unseen matter that effectively plays the role of dark matter. That is a demanding checklist. For dark matter, the decisive evidence would be a direct or indirect detection of the particle or object making it up, confirmed by multiple methods and consistent with cosmic observations. That has not happened yet. This is why modified gravity remains part of the conversation. Dark matter is strongly supported gravitationally, but its physical identity remains unknown. As long as the particle is missing, the question of whether gravity is fooling us remains scientifically alive, even if most evidence currently favours dark matter. The emotional pull of modified gravity is easy to understand. It would be profound to discover that galaxies are not hiding mass, but revealing a new law. It would echo the transition from Newton to Einstein, another moment when strange celestial motion pointed toward deeper physics. It would mean that the universe was not filled with an unknown substance after all, but that gravity itself had a hidden side. That is a beautiful possibility. The emotional pull of dark matter is also strong. It would mean that the universe contains a vast unseen form of matter, unlike atoms, a hidden majority that shaped cosmic history. It would open a new sector of physics and reveal that the familiar material world is only a small part of the matter story. That too is beautiful. The fact that both possibilities are beautiful is not evidence for either, but it does make the mystery pleasant company in the late evening. When scientists compare the two broad approaches, they often use a practical standard. Which explanation accounts for the most observations with the fewest problems? Right now, the dark matter picture does extremely well across the largest range of evidence. It explains the cosmic microwave background, large-scale structure, galaxy clusters, lensing, and galaxy formation in a common framework. It still has open questions, especially on small galactic scales and in the lack of particle detection, but it is powerful. Modified gravity explains some galaxy regularities very well, but has more trouble with clusters, lensing separations, and early universe cosmology. That is why dark matter remains the leading view. Yet leading view does not mean final answer. The universe is under no obligation to be settled by our current confidence. There are examples in science where the dominant explanation succeeded, and examples where it eventually gave way. The correct attitude is neither stubborn certainty nor endless doubt. It is disciplined openness. Dark matter is the best supported framework, but gravity must continue to be tested. Modified gravity may not replace dark matter, but it may reveal where our models are incomplete. In everyday life, gravity feels simple. Drop something and it falls. Sit in a chair and the chair pushes back. The moon orbits Earth, Earth orbits the sun, and everything seems reassuringly predictable. But gravity is also the force that shapes the universe on the larger scales, and it is the force most deeply tied to the structure of space and time. It is familiar in experience and mysterious in theory. We still do not have a complete quantum theory of gravity. We still do not fully understand how gravity fits with the other forces at the deepest level. So it would not be shocking if gravity had more to teach us. The dark matter problem sits exactly at this boundary between the known and the unknown. On one side is astrophysical evidence for unseen mass. On the other side is the possibility that our law of gravity is incomplete. The evidence leans strongly toward unseen mass, but the lack of a direct detection keeps the door from closing. The door is not wide open, but it is not locked. This is why astronomers and physicists continue to study both paths. They build dark matter detectors, but they also test gravity with galaxies, clusters, gravitational waves, pulsars, and precision measurements. They simulate dark matter halos, but they also examine whether galaxy scaling relations suggest deeper principles. They map lensing, compare cluster collisions, and refine cosmological models. The question is not settled by preference. It is settled slowly, by the universe being measured from many angles. There is a gentle lesson here about how science handles uncertainty. It does not require pretending that all ideas are equally likely. They are not. Dark matter is currently better supported than modified gravity as a complete explanation. But science also does not require pretending that a leading theory has no weaknesses. Dark matter has a missing identity. Modified gravity has missing successes. Both are studied because the truth may be more subtle than either simple story. If gravity is fooling us, it is doing so in a very sophisticated way. It must mimic the effects of dark matter in galaxy rotation. reproduce lensing, match cluster collisions, fit the early universe, guide structure formation, and explain why ordinary matter follows the patterns it does. That is a lot of fooling. If dark matter is fooling us, then it is doing so by leaving only gravitational evidence while hiding its particle nature from increasingly sensitive experiments. That is also a lot of fooling. The universe apparently is a talented magician either way. But perhaps fooling is the wrong word. The universe is not tricking us. It is simply being itself. Our theories are the attempts to describe it, and sometimes the descriptions are incomplete. When observations do not match expectations, nature is not being deceptive. It is being informative. A galaxy rotating too quickly is not a lie. A lensing map separated from hot gas is not a prank. The cosmic microwave background is not teasing us. These are clues. They are patient, consistent, and available to anyone willing to measure carefully. For now, the clues still point most strongly toward dark matter as a real component of the universe. But the question of gravity remains valuable because it keeps the interpretation honest. It reminds us that unseen matter is an inference, not a photograph. It reminds us that laws tested in one regime must be tested in others. It reminds us that a successful theory should explain not only the broad universe, but the fine details of galaxies. And it reminds us that the deepest advances often come when someone asks whether the obvious conclusion might be hiding a deeper one. So as we move toward the larger meaning of dark matter, it is worth carrying both thoughts gently. Perhaps the universe is filled with a hidden form of matter that built the cosmic web and wrapped galaxies in invisible halos. Perhaps gravity itself has a subtle face that appears only where accelerations are tiny and distances immense. Perhaps some future theory will make the debate look different from both sides, showing how matter and gravity together create the patterns we now struggle to explain. The night sky does not reveal which answer is correct at a glance. It offers stars, galaxies, clusters, arcs of bent light, and ancient radiation, each carrying part of the message. We gather those messages and test them against our ideas. Dark matter remains the strongest reading of the evidence, but the possibility that gravity is whispering something new has not entirely faded. It waits at the edge of the discussion, not loud enough to overturn the standard picture, but too interesting to ignore. And with that thought, the mystery becomes broader than a search for a particle. It becomes a question about how the universe is held together at all, whether by unseen matter, deeper gravity, or some connection not yet understood. The structure around us is not accidental. Galaxies turn, clusters gather, light bends, the cosmic web stretches across the dark. Something is shaping it all, and the answer will change not only what we think dark matter is, but what we mean when we say we understand the universe. After asking whether dark matter is a hidden substance, or whether gravity itself is whispering a deeper rule, the mind naturally drifts toward a larger question. If dark matter has helped shape galaxies, clusters, and the cosmic web from the beginning, then what role does it play in what comes next? The universe is not frozen in place. Galaxies continue to move. Clusters keep growing. Stars are born, age, and die. Space itself expands. The cosmos has a history, and because it has a history, it also has a future. Dark matter is woven into both. To understand what dark matter means for the fate of the cosmos, it helps to begin with what it has already done. It is easy to think of dark matter as a missing ingredient in the present-day universe, something we need to explain why galaxies rotate too quickly, or why clusters bend light so strongly. But dark matter is not merely a modern accounting problem. It has been involved since the universe was young. Long before the sun existed, long before Earth cooled, long before any living thing looked upward and wondered why the night was dark, dark matter was helping tiny density variations grow into structure. It gave ordinary matter places to fall. It helped build gravitational wells. It made the universe clumpier, richer, and more capable of forming galaxies. Without dark matter, the visible universe would likely look very different. Ordinary matter alone would have struggled to gather quickly enough after the early hot phase. The first galaxies may have formed later, fewer structures may have emerged, and the cosmic web might have been far less developed. The stars we see did not form in isolation from the dark. They formed in a universe where dark matter had already shaped the terrain. In that sense, dark matter is part of the reason there is a cosmic story to tell at all. It does not shine in the story, but it helps provide the setting. The future of the universe, however, is not controlled by dark matter alone. There is another major player, even more mysterious in some ways, called dark energy. Dark matter pulls. Dark energy, in the simplest description, drives the accelerated expansion of space. The names sound like relatives, perhaps two quiet cousins seated at opposite ends of a cosmic dinner table. But they are very different ideas. Dark matter behaves like matter. It clusters under gravity. It gathers around galaxies. It helps form structure. Dark energy does not seem to clump in the same way. It appears to be spread smoothly through space and to influence the expansion of the universe itself. This distinction matters because the fate of the cosmos depends on a contest between gravitational attraction and cosmic expansion. Matter, including dark matter, pulls things together. It slows expansion and builds structure. Dark energy pushes the expansion to accelerate, making distant galaxies recede faster over time. The universe we observe today seems to be in an era where dark energy dominates the overall expansion, while dark matter remains crucial inside galaxies, clusters, and the cosmic web. The universe is still full of gravitationally bound structures, but the large-scale expansion is increasingly governed by something that acts very differently from matter. Dark matter, therefore, has a double role in the future. Locally, it continues to hold galaxies and clusters together. Globally, it is no longer the dominant driver of cosmic expansion. The universe is expanding in a way that dark matter alone cannot reverse, at least in the standard picture. This means that dark matter helped build the grand structures, but dark energy may increasingly isolate them from one another. Picture the cosmic web as a vast network of illuminated towns connected by dark roads. In the earlier universe, gravity was busy drawing matter along those roads, forming larger cities and denser knots. Dark matter deepened the paths and intersections, but as expansion accelerates, the most distant towns are carried away from one another faster and faster. The local neighbourhoods remain bound. Galaxies within groups and clusters may continue interacting and merging, but far beyond those bound regions, other clusters will drift out of reach, not because they are moving through space in the ordinary sense, but because the space between them keeps expanding. For our own cosmic neighbourhood, dark matter will remain important. The Milky Way and the Andromeda Galaxy are moving toward each other and are expected to merge in the distant future. This future collision is not caused by dark matter alone, but dark matter halos are deeply involved. The two galaxies do not merely consist of their bright disks of stars. Each sits within a large dark halo. These halos extend far beyond the visible edges of the galaxies, and they may already be interacting gravitationally. As the galaxies approach, their dark matter halos will overlap, exchange energy, and help shape the merger. The stars themselves are so widely spaced that direct stellar collisions will be rare, but the gravitational structure of the galaxies will be transformed. The result will likely be a larger galaxy, perhaps elliptical in shape, surrounded by a merged dark matter halo. The familiar spiral structure of the Milky Way will not last forever. The night sky, if any observers exist then, would change over immense timescales. Andromeda would grow larger, stars would be thrown into new orbits, gas would be stirred, and new star formation might be triggered before eventually fading. Dark matter would be part of the invisible choreography, guiding the long gravitational dance. This is one way dark matter affects the future. It determines how galaxies merge, how satellite galaxies are stripped and absorbed, how stellar streams form, and how the outer halos of galaxies evolve. In the deep future, local structures may continue to rearrange under the influence of dark matter long after the wider universe has become more isolated by expansion. Dark matter does not stop time. It does not prevent stars from aging, but it shapes the gravitational containers in which stars live out their lives. On cluster scales, dark matter will continue to dominate the mass of many bound systems. Galaxy clusters that are already gravitationally bound will remain together despite cosmic expansion. Their galaxies will orbit, interact, and sometimes merge. Their hot gas will slowly evolve. Their dark matter halos will remain as enormous invisible reservoirs of gravity. Over long periods, clusters may become more relaxed, with matter settling into stable distributions. But they will also become increasingly isolated from other clusters as the expansion of the universe accelerates. The cosmic web may freeze into separated islands of bound structure surrounded by ever-growing emptiness. This future is sometimes described as lonely, but only from the perspective of beings who like a crowded sky. If dark energy remains constant in the simplest way, distant galaxies outside our local gravitationally bound region will eventually recede so far and so fast that their light will no longer reach future observers. The wider universe will fade from view. A civilization living in the far future might see only its own merged local galaxy, and perhaps a few bound companions. The evidence for the cosmic web, distant galaxies, and even the expansion history of the universe could become much harder to detect. The cosmos would not actually become small, but the observable portion would become emptier. Dark matter would still be there in those bound structures, but its great cosmic role as a builder of visible large-scale structure would be mostly complete. It would be like the foundation of an ancient city after the roads to other cities have vanished beyond the horizon. Still present, still important, but no longer actively connecting the visible universe in the same way. There is another way to think about dark matter and fate. Dark matter affects whether structures collapse, merge, or remain stable. The amount of dark matter in the universe helped determine how quickly galaxies and clusters formed. If there had been much less dark matter, the universe might have remained smoother for longer, perhaps forming fewer galaxies before dark energy took over. If there had been much more, structure formation might have been more intense, perhaps producing a universe with different galaxy sizes, different merger histories, and different conditions for stars and planets. The amount of dark matter is part of the reason our universe has its particular balance between structure and emptiness. That balance matters for life, at least in the broadest sense. Life as we know it requires stars to make heavy elements, planets to form from those elements, stable environments to last long enough for chemistry to become complex, and galaxies that are not too chaotic everywhere all the time. Dark matter does not directly make carbon, oxygen, or oceans. It does not glow warmly on a planet. But by shaping galaxies and enabling structure formation, it indirectly helped create the conditions in which stars and planets could exist. Its influence is remote but foundational. This can feel strange, because dark matter is so unlike the matter of everyday life. It does not form cells, rocks, clouds, or bread. It does not take part in the chemistry of living things. Yet without it, the cosmic architecture that led to living things might have been very different. We are made of ordinary matter, but ordinary matter came to rest inside dark matter wells. We are children of atoms, but those atoms gathered into galaxies partly because of an invisible substance that atoms cannot easily touch. In the far future, stars will slowly exhaust their fuel. The most massive stars die quickly, in cosmic terms, while smaller stars can burn for enormous lengths of time. Over time, star formation will decline as gas is used up, heated or locked away. Galaxies will grow dimmer as bright young stars become rare. Long-lived red dwarf stars may continue shining for trillions of years, far beyond the current age of the universe. Dark matter halos will remain, but they will not provide fresh fuel for stars. They shape gravity, not nuclear burning. They can hold galaxies together, but but they cannot stop stellar evolution. This is an important distinction. Dark matter helps build and bind cosmic structures, but it is not an energy source for ordinary stars. It is not a hidden reservoir of light waiting to turn on. Unless dark matter has interactions we have not discovered that allow it to decay, annihilate, or otherwise produce energy, it will remain mostly dark. In some models, dark matter particles can annihilate or decay very slowly, producing radiation over time. Scientists search for such signals today. If dark matter had such processes, they might affect the very long-term future in subtle ways. But for many models, dark matter is stable and quiet, continuing to gravitate without brightening the cosmos. Could dark matter itself eventually collapse into black holes or compact structures? In the standard picture, not efficiently. Ordinary matter collapses because it can lose energy by radiating light. Gas clouds cool, shrink, and form dense objects. Dark matter seems unable to radiate energy in that way, so it cannot easily settle into compact clumps beyond the structure's gravity already forms. It remains in diffuse halos. Some dark matter can be captured by stars or planets if it interacts weakly with ordinary matter, but the effects are usually expected to be small. If dark matter has stronger self-interactions or hidden cooling mechanisms, the future could be more complicated, but observations limit how much this can occur for the dominant component. Dark matter halos themselves evolve. Through mergers, tidal stripping, and gravitational encounters, they change shape and distribution. Small halos fall into larger halos. Some are torn apart. Streams of stars and dark matter wrap around galaxies. The outer regions of halos extend far beyond visible disks, and their boundaries are not sharp walls. Over vast times, gravitational interactions can slowly rearrange matter. But in an expanding universe dominated by dark energy, the largest new mergers between distant clusters become less likely. Structures not already bound will drift apart. The era of grand cosmic assembly will gradually give way to an era of local evolution. The fate of dark matter also depends on its identity. If dark matter is made of WIMPs, or similar particles, then in some models particles and antiparticles may be the same, allowing them to annihilate when they meet. In dense regions, this could produce a faint trickle of radiation. Over unimaginably long times, if annihilation is possible, dark matter in the densest places might slowly diminish. But halos are diffuse, and annihilation rates would usually be extremely low unless the particle properties allow stronger effects. If dark matter is made of axions, its future might be more like a stable field persisting across cosmic time. If it is made of primordial black holes, those black holes would have their own long-term evolution, including possible evaporation over immense timescales if small enough, or continued gravitational interactions if large. If it is a mixture, the future becomes a layered story. This is why discovering what dark matter is would not only explain the past, it would clarify the future. The particle or object identity determines whether dark matter is perfectly stable, whether it can decay, whether it can annihilate, whether it interacts with itself, and whether it can form smaller structures than we currently expect. Each property changes the long-term destiny of cosmic structures. Dark matter is not just a missing label in a cosmic inventory. It is a clue to how the universe will age. There is also a deeper connection between dark matter and the ultimate geometry of the universe. In older cosmological discussions before dark energy was discovered to dominate the expansion, scientists often asked whether the universe contained enough matter to stop expanding and eventually collapse. Matter pulls inward through gravity. A universe with enough matter might slow, halt, and reverse expansion in a great collapse. A universe with too little matter would expand forever. Dark matter was therefore central to the question of cosmic fate. How much unseen mass existed? Was there enough to close the universe gravitationally? Modern observations change that picture. The expansion is not merely continuing, it is accelerating. Dark energy appears to dominate the large-scale future. the total matter content, including dark matter, is not enough to reverse expansion under the standard model. The fate seems to be continued expansion, with structures outside bound regions receding ever farther. Still, dark matter remains part of the calculation. It contributes to the total mass and affects the expansion history. It shaped the transition from the matter-dominated era, when structure formation flourished, to the dark energy-dominated era, when expansion began to pull the large-scale universe apart faster. In other words, dark matter ruled much of the universe's middle history. Radiation dominated the earliest era. Matter, especially dark matter, then became the main driver of gravitational structure growth. Later, dark energy became dominant in the expansion. The universe's story can be thought of as a sequence of changing influences: light and radiation first, matter and gravity next, accelerated expansion later. Dark matter is the great architect of the era in which galaxies and clusters formed. That title is not too grand. The universe we see, the galaxies in deep images, the clusters connected by filaments, the vast cosmic web, all belong to the matter-shaped era. Dark matter made that era possible in its present form. Its future role may be quieter, but the structures it helped create will persist for immense times. The fate of the cosmos can sound bleak when described in terms of fading stars and accelerating expansion, distant galaxies disappearing beyond reach, star formation slowing, the night sky growing emptier for future observers. But there is another way to hear it. The universe is changing according to deep laws and hidden ingredients we are still learning to understand. Its future is not a simple curtain falling. It is a long transformation. Local galaxies merge into new forms. Stars continue to shine for extraordinary durations. Dark matter halos remain as vast gravitational archives of the past. The cosmic web, even as it becomes harder to observe from any one place, remains part of the universe's history. Dark matter also raises the possibility that the universe contains more hidden complexity than we know. If there is a dark sector with multiple particles or forces, then the far future may include processes we have not imagined. Perhaps some dark particles decay slowly. Perhaps dark matter self-interactions change halo structures over time. Perhaps dark matter connects faintly to other fields. Perhaps the identity of dark matter will reveal a bridge to physics beyond the known forces. In that case, the fate of the cosmos may depend on properties not yet measured. The future is not only distant, it is scientifically incomplete. This incompleteness is not a failure, it is part of the wonder. A finished universe would be simpler to describe, but perhaps less interesting to inhabit. The unknown invites careful attention. Dark matter, by remaining unidentified, keeps the future partly open. We can outline the broad fate under current models, but the details wait for discovery. Consider the possibility that dark matter is unstable over incredibly long times. If it decays into lighter particles, then halos might slowly lose mass. Galaxies and clusters could gradually become less tightly bound. The expansion history might be affected depending on the decay products and timescales. Observations already constrain many such possibilities, because decays occurring too often would produce radiation or alter structure in ways we would notice. But extremely slow processes remain possible. A particle that seems stable across the current age of the universe might still decay over times far beyond ordinary imagination. If so, dark matter's future would not be eternal stillness, but a near-silent transformation. If dark matter can annihilate, the densest regions might very slowly convert some dark matter into radiation. This could produce faint signals today, and perhaps contribute tiny amounts of energy in the future. But again, the effect depends on the particle. Some candidates do not annihilate in meaningful ways. Some are their own antiparticles, some are not. Some have interactions that are too weak to matter except in special environments. The fate of dark matter is tied to its nature, and its nature is still hidden. If dark matter is made of axions or ultralight fields, it may have collective behaviours that affect structure over long periods. Axion, like dark matter, could form dense configurations in some circumstances, sometimes imagined as clumps or star-like objects made of the field itself. Whether such objects exist and how important they are depends on the details. If they do exist, they could influence gravitational lensing, stellar motions, or other observables. Their future would be different from that of a simple swarm of heavy particles. Again, identity matters. Primordial black holes, if they contribute significantly, would bring another kind of future. Black holes can merge, orbit, disrupt nearby systems, and emit gravitational waves when they collide. Very small black holes would evaporate through quantum processes over time, while larger ones could last far longer than the current age of the universe. If dark matter were partly primordial black holes, then the future dark matter story would include a population of ancient compact objects moving through halos. But because observations strongly limit many possible populations, this remains a constrained possibility rather than the default. The standard picture, with stable cold dark matter and dark energy driving accelerated expansion, gives a fairly clear broad future. Bound structures remain bound, unbound structures separate, galaxies in local groups merge, star formation declines, the observable universe from any given location becomes increasingly dominated by nearby bound matter. Dark matter halos persist, shaping the motion of stars and remnants long after bright galaxies have changed form. The cosmos becomes darker, not because dark matter grows stronger, but because stars fade and distant light becomes unreachable. There is a quiet symmetry in that. Dark matter began as something that did not shine but helped light gather. In the far future, as starlight fades and distant galaxies disappear from view, the universe may become darker in an ordinary visual sense, while dark matter remains as it always was, unseen but present. It will have helped build the stage, watched the lights come on, and then remained after many of those lights dimmed. This does not mean dark matter has intention, of course. It is not a watcher. It does not plan or remember. These are human images we use to make vast timescales bearable. But scientifically, its persistence matters. The gravitational structures it forms are long-lived. The halos around galaxies are not temporary decorations. They are enduring components of cosmic architecture. For future astronomers, if they exist far from now, dark matter may be both easier and harder to infer. Easier because local structures will still show gravitational effects. Stars and remnants will still orbit within dark halos. Harder because the broader cosmological context may fade from view. If distant galaxies disappear beyond the observable horizon, future observers may not easily see the expansion history or the cosmic web in the way we can. They might live inside a merged galaxy and find it difficult to reconstruct the universe's larger structure. The present era may be unusually rich for cosmology, with the cosmic microwave background still observable, distant galaxies still visible, and dark matter's influence measurable across many scales. That is a humbling thought. We're not only made of ordinary matter in a dark matter universe, we also live at a time when the universe is still generous with evidence. The cosmic web can be mapped, the ancient light can be measured, galaxies at many distances can be observed. Dark matter has not revealed its particle identity, but it has left many gravitational clues still accessible to us. Future observers may not have the same cosmic view. The universe changes what it allows to be known from any one time and place. Dark matter also affects the fate of individual galaxies through satellite systems. Small galaxies orbit larger ones, losing matter as tides pull them apart. Their dark matter halos are stripped first, then stars may be drawn into long streams. These streams become records of past interactions. Over time, large galaxies grow by absorbing smaller ones. The Milky Way has already done this many times. It is doing it still. Dark matter governs much of this process because it dominates the mass of small galaxies and controls the gravitational environment of the larger halo. The future of a galaxy is partly a history of what its dark matter halo captures, strips, and absorbs. The outskirts of galaxies will continue to be shaped by these interactions. Stellar streams will wrap around halos. Remnants of dwarf galaxies will dissolve. Dark subhalos may disturb or thicken structures. The visible galaxy will carry signs of invisible encounters. Long after the bright spiral arms of the Milky Way are altered by merger, the dark halo will contain traces of the assembly history. It will be less like a smooth sphere and more like a layered archive, though one written in gravity rather than ink. The fate of the cosmos is therefore not only about expansion, it is also about memory. Dark matter halos remember how structures formed. Their shapes, substructures, and motions preserve information about mergers and growth. Even now, astronomers read these gravitational memories through stellar streams, satellite galaxies, and lensing. In the future, such memories will continue to shape what remains locally, even as the larger universe recedes. There is a personal scale hidden inside all of this. We are temporary beings in a universe evolving over times that dwarf biological life. Dark matter will outlast our species unless it has properties no one yet knows. It helped assemble the galaxy before Earth existed, and will remain after the sun changes beyond recognition. That might make human life feel small, but it can also make it feel precious. We are brief arrangements of ordinary matter capable of studying a hidden component that has shaped billions of years of cosmic history. For a little while, atoms inside a dark matter halo became curious enough to ask what the halo is made of. That is one of the loveliest oddities of cosmology. The universe makes observers from a minor ingredient. Ordinary matter is not the dominant matter, yet it forms stars, planets, chemistry, and thought. Dark matter is more abundant, but it does not make notebooks, telescopes, or sleepy science videos. The smaller component becomes aware of the larger one. The luminous matter studies the dark. What dark matter means for the fate of the cosmos is therefore partly physical and partly philosophical, though still grounded in evidence. Physically, it means that the future of galaxies and clusters is governed by invisible mass as well as visible matter. It means the large-scale structure we inherited from the early universe will evolve within dark halos and filaments. It means bound systems will persist while expansion carries unbound systems apart. It means the identity of dark matter could alter the details of cosmic aging, from halo stability to possible decay or annihilation. It means the future cannot be fully understood until the hidden matter is understood. But it also means that the universe is not simply a story of light. Light is what reaches our eyes and telescopes most directly. Light is how stars announce themselves. Light is how galaxies become visible. Yet gravity tells us that much of the story has always been written in darkness. The fate of the cosmos belongs to both: the glowing stars that age and fade, the dark halos that hold and guide, the expanding space that separates, the unknown energy that accelerates, the hidden matter that built the stage and remains in the wings. As the universe continues to expand, dark matter will not stop the acceleration on the larger scales if the standard model remains correct. It will not pull all galaxies back together into a final collapse. It will not keep distant clusters visible forever, but it will continue to shape every gravitationally bound island. It will determine how galaxies merge, how stars orbit, how remnants move, how clusters hold together, and how local cosmic history unfolds. Its power is not ultimate control over expansion, but deep influence over structure. Perhaps one day scientists will finally identify it. A detector may record the right kind of event. An axion experiment may hear the faint signal it has tuned toward for years. A telescope may find a pattern no ordinary source can mimic. A collider may produce an invisible particle whose properties match the sky. Or perhaps the answer will emerge from a combination of small clues, none decisive alone, but together unmistakable. When that happens, the fate of the cosmos will become clearer. We will know whether dark matter is stable forever, whether it has hidden interactions, whether it belongs to a wider dark sector, whether it can slowly transform, and how it shaped the first structures. Until then, dark matter remains both an answer and a question. It answers why galaxies rotate as they do, why clusters hold together, why the cosmic web grew. But it asks what most matter is, how it began, how it behaves in detail, and what it will become. It is one of the rare scientific ideas that explains much while remaining deeply mysterious itself. The night sky above us is filled with stars, but the future of the universe is not written by stars alone. It is written by the invisible halos around galaxies, by the dark filaments between clusters, by the expansion of space, by the quiet decline of star formation, and by the unknown properties of matter we have not yet touched. The fate of the cosmos is not a simple ending. It is a long unfolding shaped by ingredients both seen and unseen. So when we think of dark matter, it may help not to imagine only emptiness or absence. Dark matter is not a hole in our knowledge only. It is a presence in the universe. It is the unseen mass that helped gather the first galaxies, the hidden structure that still surrounds our own, the gravitational partner of every bright object we admire. Its future is tied to the future of all bound things. Long after today's constellations have shifted beyond recognition, long after the Milky Way and Andromeda have become something new, long after many bright stars have faded into remnants, the dark halo will still shape the motions of what remains. And somewhere within that long story, for this brief calm moment, we are here, made of ordinary matter, resting inside a galaxy held partly by dark matter, thinking about the fate of a universe whose largest ingredients we are still learning to name. The mystery does not need to be solved tonight to be meaningful. It is enough to follow the evidence gently, from stars to galaxies, from galaxies to the cosmic web, from hidden particles to the far future. The darkness around the universe is not empty. It is full of gravity, history, and unanswered questions, quietly holding the shape of everything that shines.